All right, let's get started. So today we have the privilege of two chalkboard talks, one by Jared Goldberg, who you'll hear right now, and Anna Ho later in the morning. So today's theme is core collapse supernovae. Yesterday, as you know, we covered a lot of different grounds, different types of transients, where they live in the phase space of transients. But starting today, we'll go into individual objects and classes and try to understand what the unsolved questions are and how do we make progress. So the funny thing is that it's a sort of an anecdote, which is that Jared, Anna, and I, we were all part of this a very similar school when we were all grad students, like exactly where you guys are now. And Anna and I, we went to grad school together, and I was the entire idea for this school. In fact, came when I was texting Anna. I was just Anna and I, we were talking, and then we were thinking about how enriching that experience was when we were in grad school, because we all sort of have heard of a lot of the theories, and we sort of have an idea of the models that we are working on, but it's schools like this where I feel you suddenly get this click, like, oh, that's how it works. And I think it's really those realizations that I think made the school that we were at very enriching experience, and we're trying to sort of enhance on that in this particular event. So so that's sort of a background of why it's funny that all three of us are now sort of on the other side right now. So okay, good. So we will get started with our first lecture. So our first lecturer is Jared Goldberg. Jared did his undergrad at Claremont McKenna College and then went on to do his PhD at UC Santa Barbara, and since then has been a Flatiron Research Fellow at the CCA, and he'll be telling us today about the theory of core collapse supernovae.
All right, great. Thank you. I am honored and a little intimidated to be here. Many of you are experts in the thing I am about to talk about, but hopefully we can talk in broad strokes and get the room on the same page. Some of what I'm going to go over is what we talked about yesterday. Some of the equations will look familiar from Brian Metzger's slides, but it's also always good to say things out loud, force ourselves to slow down and write some things on the chalkboard. Feel free to take notes, feel free to ask questions. If something is unclear, please let me know. This is, it's good when this is a conversation. I will probably make you talk to each other a little bit. Part of the point of these workshops is also to get to know the people around you. So I'm just warning you now. And I have kind of 4 overarching objectives or goals for today. Number 1 is just to give an overview of core collapse supernovae, primarily from this theorist's perspective. Right? How does it happen? Why does it happen? When does it happen? And then 2, what does it look like? What are the different subclasses? How do different kinds of exploding stars manifest themselves in the properties of the light curves and velocities and things we can observe? 3, I want to again build upon the physical intuition for what sets those observables. So things like the luminosity, the velocity, the duration of these transients. So let's call that physics. And then 4, probably at the end, to give some insight into what big data, what the next frontiers, what can we do in light of this physics, but in light of all of the other complexities that come with modeling in detail, right? So why is Rubin so exciting? What are we, what do we hope to learn from a bunch of these things? Let's say population question mark. And I will also preface this with, I'm pretty jet lagged right now. So if I start to ramble or stop making sense, don't hold it too much against me. All right, so I come from a stars background, and I think of core collapse as the culmination of one of the most exciting processes in the universe, which is the life and death of a massive star. So we all remember, hopefully, from our picture of star formation, that a star starts as a ball of gas and collapses somewhat. It may be accreting, it may have a disk, that's not important for this. It compresses at the center, and the whole ball of gas compresses, it heats up, and you start to ignite hydrogen that prevents that gravitational collapse. Right? A star is a constant battle of an outward pressure support and luminosity, or that's the outward pressure support generated by luminosity and the force of gravity pulling it. Over time, you run out of hydrogen in the core of your massive star, and you start to fuse heavier and heavier and heavier elements. You fuse the hydrogen into helium, the helium into carbon, the carbon and some helium into oxygen, neon, magnesium, silicon, you go up until you get to iron. Right? So at that time, your envelope expands as your core contracts, and this becomes the red supergiant phase. The core of the star also keeps evolving in a weird way. So here's the density of the core versus the temperature of the core of the star. Stellar physicists love to draw this diagram. I'm going to put some numbers here. This is 10 to the 6. This is 10 to the 10. These are in grams per centimeter cubed. I guess this is rho, not log rho, but. And here's something like 10 to the 9, 10 to the 10. So we only even approach central temperatures of 10 to the 9 in slightly more advanced stages of burning. But you see that the core gets hotter and denser. At some point, though, it starts to do some little wiggles. This one goes down a little bit. Okay. And the first time I saw that when I was running a stellar evolution code, I was like, this is wrong. Something is going bad with my models. But actually, this is what happens. So here, an excursion in this diagram, it tells you something about the core contracting or expanding or heating up, getting denser or less dense. So here, for example, we are getting hotter and denser. The core is contracting and it's heating. At some point, then, you remain at roughly fixed temperature, and your density changes. This is because you've started burning, so you start injecting heat. You start to act, well, here actually I think comes from neutrino losses as you contract. Here you start to inject heat, you get, you keep your burning at sort of a fixed temperature. You go to lower densities because your core actually expands in order to accommodate that injected heat and so on. But you get all these wiggles. And as these nuclear reactions increase, the neutrino luminosity also increases, right? You have hotter and hotter and hotter, denser and denser and denser environments. These reactions become more vigorous. The neutrinos emerge from these nuclear reactions. The neutrinos stream out of the star, and they start to cool the star. And at this time also, the iron core starts to grow. So there's a famous plot you might often see in a stars class, which is the energy per nucleon versus the atomic number or the mass number. And you'll see a kind of peak here. This peak is around iron, cobalt, nickel. Oh, iron, nickel, cobalt. After this point, it's only marginally or not at all energetically favorable to keep fusing. So your iron core grows and grows and grows. In this limit, as you have an iron core, Degeneracy pressure, the pressure that from the quantum mechanical fact that you can't put electrons in the same state at the same time in the same quantum mechanical state, that actually provides most of the pressure support for the star. And the only thing you really need to know about degeneracy pressure, well, there are more things depending on your point, or depending on what you're trying to do, but here, your degeneracy pressure is not sensitive to the temperature. Well, why does this matter? As your core grows, as your iron core grows, you no longer have a way that when the temperature increases, you expand to cool to accommodate that. Rather, you just get hotter and hotter and hotter. This process is why white dwarfs explode, because as you add mass to them, you get hotter and hotter and hotter. Those are supported by electron degeneracy pressure, and they get hotter and hotter and hotter. And then, for a white dwarf, you maybe ignite some of the carbon and oxygen in the white dwarf. That adds heat. The temperature does not respond, so it doesn't cool down. In fact, you add heat, it gets hotter. So the temperature goes up, so your nuclear reaction rate goes up. So you get more heat, so you get more hotter, so you get more heat. And that process ends up exploding the star. In this case, you don't get energy out either. And so at some point, you have a balance between your pressure gradient and and gravity, right? Above a certain rho, your pressure gradient cannot accommodate that. As you march up this as you march up in central density, you can kind of no longer get this to win. So likewise, the core collapses, but here, instead of exploding as a supernova, well, instead of exploding as a thermonuclear supernova, the core collapses and turns into a neutron star, or if it's above a certain mass limit, a black hole.
Sorry, Jared, at this point in
Yes.
the core, it's still electron degeneracy pressure before it collapses.
It's electron degeneracy pressure to first order. It's an iron core, so you also have protons, and you also have a little bit of heat and entropy from the fact that the star is still hot. So there's a few more things going on in there. That's actually, if you were to just write down the degeneracy pressure, you would find a lower Chandrasekhar mass for the protons and electron gas that is the iron core than most of the electrons that are the relativistic particles in the white dwarf case.
Over what time scale does this evolution happen from like 10 to 6?
Right. At here, so I'll label a few more things. Here's your silicon burning. Here's oxygen's here, carbon's down here. Here you have about 2 hours left until you collapse fully. Up here, once you've kind of finished silicon burning, you have maybe a minute. So now we have this wonderful collapse where we go from roughly the radius of the Earth, which is something like 10 to the 4 kilometers, down to the radius of a protoneutron star, which is about 100 kilometers. So 2 orders of magnitude in, well, how long you can kind of write down a free fall time that goes something like 1 over the square root of the density times gravity. Actually, that's more of a sim than a proportional to. Right, if we here's sort of it's the dynamical time. It's balance mv squared is gravity, something like that, and your time is r over v. This gives you your time scale. So we can plug in some numbers, and for 10 to the 10 centimeters, you have about a solar mass. Wait. Oh, okay. Do this real time. So for 10 to the 10 centimeters, you have about a solar mass, or 10 solar masses, which is 10 to the 34 grams. Your 10 to the 10 centimeters cubed is about 10 to the 30. G, so this is something like G is something like 10 to the minus 9. So you have something like, here's 4 orders of magnitude minus 5. So you have 1 over the square root of 10 to the 5 or so. So, but yeah, you're right. Okay, that gets me closer to what I wanted, which is good. All right, so you have kind of 4 minus 7 minus 3 or so becomes something like, well, something like 30 seconds. Well, something like the square root of 1,000. When I originally did this, I had something.
I think the 10, I think it should be like more like a second, but I think it's fixed if you replace the solar radius cubed downstairs by the Earth radius cubed.
Ah, yes.
Yeah. So I think it's of order a second. Yeah. But I think that's
That makes sense.
Yeah.
Okay. You get an extra 6 orders of magnitude up here, right?
But then,
So it's somewhere in between the 100 and the
well, it's
I was doing-
10 to the 9 cubed downstairs instead of 10 to the 10 cubed.
Yes.
Yeah, so it's 27. So it's like
This is, yeah, okay. So then you get your 4 over 7 becomes
yeah, so that's 3, 4, 5, 6.
10 to the 7. It's roughly a second.
Yeah, great.
Thank you.
Great.
It's a problem when you write your notes late at night. There's a typo.
And jet lag.
And jet lagged, yeah. Okay,
So we figured it out.
we figured it out. Ultimately, this process takes about a second. Now, for the material farther out, as the radius is larger, the dynamical time is correspondingly larger. So the stuff that's in the innermost layers starts to fall first. And then the rest of the star continues to fall in. Now, because of these layers of nuclear fusion that gets you this core that becomes like an ogre or an onion with layers, your core, this is just some outward coordinate. Your core has a bunch of different layers. And then your envelope. Big, puffy, very dense. And this now gets denser and denser as this falls in. And all of this stuff starts to fall in. So this density kind of starts to shoot up as this all moves in. Now, at some point, you have the protoneutron star. So all of the material that's falling in bounces off the protoneutron star. This starts to form a stalled shock. But just like you can't drop a ball and have it bounce higher than you dropped it, the stuff that bounces off the protoneutron star kind of stalls while the rest of the material is falling in on its head. This was the big problem, maybe even in kind of the early 2000s and 2010, is like, how does that stalled shock revival even work? Because we know stars explode after this because we see them explode. But we still have to provide the extra energy into this ejecta or into the rest of the star in order to cause it to become unbound ejecta, in order to cause the star to explode. So what happens? Well, it turns out that there's something like 10 to the 53 ergs of neutrinos that are produced in this process. That's a lot of energy in neutrinos. But we know, hopefully, that neutrinos are pretty weakly interacting particles. But this is a really, really dense environment. So, it's possible that some fraction of the neutrinos can couple with the matter and cause this to happen. The binding energy of the star is something like 10 to the 49 to 10 to the 50 ergs. So if you can couple about 1% or 0.1% of the neutrinos, that may be enough to overcome the binding energy and cause the star to explode. Right? So, side note, when exactly does this shock revive? This is complicated because the way that these neutrinos couple with this, you can actually write it down kind of like a problem where you have radiative diffusion through some material, and you can even write down a kind of mixing length theory like, for the stars folks in the rooms, you can write down a mixing length theory like prescription where you consider how much flux is being carried by neutrinos, how much flux gets carried by a sort of bulk motion of the fluid, i.e. kinetic energy, i.e. some amount of, or advective flux. And you can write down a sort of balance. You end up finding that this additional turbulence generated by the neutrinos is important, at least, in reviving the shock. This also is sensitive to things like magnetohydrodynamics and all of your other complicated physics that you want to wave away with an expression. But overall, I'm going to zoom in here. The most important controlling parameter in the last decade or so has emerged to be how steep this profile is at the very base, kind of in the silicon interface, the iron silicon region, and also the silicon oxygen interface. And what that really tells you, the steepness of this, is if we have infalling material that exerts some ram pressure that goes something like the rho v infall squared, you have a shock that's trying to get out. If all of a sudden the density above it plummets and you can just move it a little bit, then there's a lot less falling on its head, so the shock can run away. If, on the other hand, the slope is more shallow, the core is in some sense less compact, more diffuse, the shock has to keep fighting all this infalling material as it tries to get out of the star. This ends up determining, to some extent, whether you get a successful explosion, make a neutron star at the center, or you have the shock stall, fall back, all the material continues to fall on. There's a hydrogen-rich envelope, you'll get a weak transient. If there is not, then you will probably just form some quiet black hole.
Can you repeat that part, please?
Yes.
The slope.
Yeah, so if the slope is shallow, the shock is trying to get out, but as it keeps traveling, it still has more and more ram pressure. It still feels more and more of the stuff falling on its head. It's being driven by some pressure outward, but there's more pressure inward that it has to overcome. If, on the other hand, this is a pretty steep interface, then you push the shock out a little bit, and all of a sudden there's a lot less falling in on it, so it can revive more easily. Again, this is, yeah.
If it's falling in, it's not the mass it's collecting.
It also has to do with the mass it's collecting. You sweep up, I think, less.
Basically, if it's sweeping up less mass in every
Yeah.
time doubles the radius.
Mhm.
So it's kind of not, it's losing energy. The shock isn't conserving isn't holding the total amount of energy in the explosion, but it's going to accelerate and then.
Yeah.
So is that actually what happens there? Like, is the shock actually
Mm.
not carrying not causally connected to the center of the star?
I think that the shock is causally, well, the center of the star is falling, the very center of the star is falling inward on very rapidly. So I think it's not causally connected to, I think it's not causally connected to the very center. I do think that it is causally connected to much of the stuff behind it. That is, the neutrinos keep kind of streaming, at least for a little bit. There's a gain region. It is more complicated than this picture. What you are saying is also, I think, part of the picture. I'm trying to give a first order.
Yeah. No, I'm just
Intuition,
trying
yeah.
to make sense of the,
Yep.
of the matter falling on its head and
Yep.
what
So
you're
in the
saying.
frame of the shock, matter falling on its head means I am sweeping up matter.
Like,
in the-
so what you're saying is in the shock frame, the
Yes.
question is, what is the mass flux moving in towards it?
What is the mass flux or the momentum flux
Or
or the
momentum
energy
flux,
flux?
yeah,
All three
um,
of these are kind of related questions. Yeah.
Okay.
Yes, Andrea.
But if I can just interject, the thing that isn't, so the sweeping up of mass is not what's adding energy behind the shock. What's pushing the
No.
shock out is the heating from the neutrinos.
The adding up of mass tells you how much mass needs to be accelerating with a given amount of
Yeah.
energy.
And this interface, it's not really the slope, it's actually a jump.
Yeah.
So there's this brief moment,
Where the shock is expanding into vacuum, effectively.
basically.
Kind of, yeah.
Because there's a huge drop off in the density. So it's more like a step function than a slope. Yeah, and so you just have this kind of brief moment where all of a sudden the neutrino heating can win, and then you're home free. But you need just a
And
very
then until
brief.
it collects an equal amount of mass. So
uh,
what it like already has.
I mean, there's so much.
Sorry.
It's-
I mean,
again, it's all-
the density of this material is so high relative to the envelope. The envelope is like spread out to Jupiter's orbit. Like,
Yeah.
Yeah,
No.
yeah.
This
Are
is
we
the-
talking about the envelope or
The core. So
the core?
about 1.5 solar mass falls in. This interface, you're right, is something like a couple more solar masses. So there's about a solar mass-ish in the gain region, and it has to sweep up about a solar mass. I like to think of this in terms of a balance of pressures because you're pushing the shock out against the stuff that's falling in. You can also think of this in terms of energy densities having to accelerate a certain mass. These are not totally equivalent pictures, but they are, I think, close enough that to first order, a pressure is an energy density, and so we still are trying to drive a shock out. Yeah, more. A few questions. Mhm.
So does this happen at every stair step where you have this to be or not to be for the core collapse being a transient we see?
Not really. So all of these other stair steps have much lower densities. And so you've already kind of successfully added enough to unbind the star. If you can unbind the star here, the rest of this is more easily unbound. That being said, when the star, so what I was going to mention next, which is a perfect segue, because I have lots to cover and it's been, I was ambitious. As the shock propagates through this, some of it does reflect off of these boundary layers. You get just like a reflection, just like you have a wave kind of hitting the, well, you have, at every interface, you have a reflected component and a component that propagates forward. That ends up seeding instabilities, in particular the Rayleigh-Taylor instability that causes mixing, in particular at these interfaces. So that does play a role. The fact that you have this cake-like structure does play a role in how this material ends up mixing. This mixes the composition, so you get core material that ends up out in the envelope. It also mixes the density, so you smooth over these profiles as the shock propagates through. But this neutrino mechanism turns off in a matter of a second or seconds. And all of this process, the rest of it, you can say, well, how long does it take the shock to travel through the star? For your explosion energy goes something like 1/2 m star v shock squared. We're going to do this one zone model thing a lot. This takes roughly the stellar radius divided by the shock, which is something like 100 to 1,000 solar radii, and the shock for an explosion energy of about 10 to the 51 ergs and a stellar mass of something like 10 solar masses. Brian mentioned the number about 4,000 kilometers per second yesterday. This is about 4,000 kilometers per second. And when you do the math, this ends up being something like a day. Right, so the neutrino mechanism, all of this stuff is happening in a second. And then you get a neutrino signal from the neutrinos that manage to stream through. Super K is happy. 87A happened. They found like 12 neutrinos. It was truly the first multi-messenger event, unless you count cosmic rays. But then a day later, you get the shock breakout. When I say shock breakout, I mean the shock reaches a depth in the star where photons can diffuse ahead of the shock. Because the shock has a finite velocity, and the photons are trying to diffuse out. I'll come back to that towards the end.
I'm sorry,
Yes.
can the proto-neutron star collapse into a black hole before the shock breakout happens if the slopey thing, because you said that
Well,
if the slope is very high, that can drive the collapse into a black hole.
so I think it takes. It's if the slope is shallow, then the shock won't get out, and then the rest of the material will fall in. That was, if the slope is steep, then the shock will drive out. Some of it depends on how massive this region is. If there's more mass in this region than a stable neutron star can support, then it'll become a black hole. So some of the more advanced 3D simulations now are showing this process, but then the mass of the iron core is already kind of above 2+ solar masses, so that will fall into a black hole. Another thing that can happen is, as the shock propagates through this, some amount of material from these reflections in the slowest moving innermost regions can become rebound as the reverse shock hits it. That material can fall onto the central object, and you get a sort of fallback black hole in a successful explosion. The time scale for producing that depends on things like how much angular momentum is in that material, because that will determine whether you circularize and form a disk that accretes, or something like that. Yeah. Okay. Yes.
When do we form, when do we get neutrinos and 10 to the 53 ergs and neutrino energy? Which step in the evolution?
The collapse itself. So as you collapse from the iron core, you have protons and electrons in the iron core. Those combine to form neutrons that make up your neutron star. But by conservation of lepton number, you also need to form neutrinos. You have two things, you need two things. So you form the neutrinos, and that's much of the process that forms the neutrinos there. It's not all electron neutrinos, and there's flavor oscillations, and people start to do lots of speculative, crazy, or detailed calculations, physics. But to first order, this is, yeah, that's kind of where it happens.
And so at which point do neutrinos couple to matter, or when do actually they interact and release the energy?
In that first split second. In that first second. The neutrinos here are trying to get out the proto-neutron star forms, the neutrinos stream out. They're trying to get through this material. Most of them stream through. Some of them churn the material that end up driving the injecting the energy that drives the shock out. Okay. Other questions? I'm going to table this process for a bit, and then we'll return to it. And now I want to talk a little bit about taxonomy. I imagine Anna is going to go into a little bit more detail, and I know that Saurabh talked about some of this yesterday, but I think it is useful. It has always been useful for me, especially when teaching, to get us all on the same page. What do we mean when we now see a supernova? Okay, all that complicated stuff happened. We know from theory it should happen, probably, but we really know because we see supernovae. That's how we know stars explode. That's the only reason we know that the shock is successful at reviving, is because in many cases we see supernovae. And there are two types of supernovae. We're going to call them type 1 and type 2. That is what the observers claim, and we will distinguish these because type 1 have no hydrogen and type 2 have hydrogen. On board so far? Okay, well, the picture becomes a little bit more complicated because we actually have a lot of these subclasses. So first, we have type 1a supernovae. These are not massive star explosions, but we don't know that from the light curve alone. They have in their spectra no hydrogen, because they're type 1, not really helium. They have strong other features, and their light curves sort of look like that. Brian mentioned yesterday that the luminosity and duration of this light curve can roughly be understood as how much energy you have in heat in this ejecta and how long it takes that heat to escape. This late time behavior is consistent with the radioactive decay chain of nickel 56 to cobalt 56 to iron 56, where the exponential decay of this is basically the cobalt decay timescale, up to some losses, because it's not, the cobalt decay is not perfectly thermalized. And Brian mentioned this has to do both with the gamma rays and also the beta decay. Anyway, we also have type 1b's and type 1c's. Type 1b's have no hydrogen, but they do have some helium. Type 1c's also have no helium. Their light curves also look like this. The primary difference here is that there's less nickel, and sometimes we do see some kind of early bump. In 1A's, as you look deeper and deeper in, you also maybe see some early bumps. In the 1A scenario, it turns out, in part because of the spectroscopic features of these, you can identify these more or less as the total thermonuclear explosions of a white dwarf. There are other 1A-like subclasses, like a 0.1A, which is an incomplete thermonuclear explosion, or a 1AX and other things. I won't get into these because today is core collapse. But for the 1BCs, the interpretation is that instead of having a big hydrogen-rich envelope that it takes the shock a day to get through, you just have a barren core, and that core collapses, explodes, and does this whole thing. You also have things like these 1C broadlines, which are just moving very, very fast. You have other things. You have these superluminous events. That means they're very, very bright. But that's kind of the main picture. So these are the core collapse ones. In type 2s, now I'm going to do something a bit controversial. I'm going to write 2B first. These are not the most common type, but they're the most similar to the ones, which is they also have a light curve that looks like this. But when you look early enough, they actually often have some early spike. The other thing is that you do see trace amounts of hydrogen that as the as time goes on, start to disappear in favor of helium. And the interpretation here is that, well, it's like this one, but there was a very low mass hydrogen envelope. So you have a big radius, and as I'll derive later, and also Brian mentioned, the bigger radius means you have a brighter explosion at early times, and so that kind of helps give you this initial spike. Okay, now we have type 2P. These start with an initial spike, but it quickly, or not too quickly, fall onto what's called a plateau. That's why they're Ps. This luminosity plateau I will explain momentarily. You also have these short plateau 2Ps. That's just when you have a plateau that's short. You have two Ls. The L means linear, but it's linear in log space, so it's more like an exponential decay. But then also sometimes you have something that looks like the end of the plateau before falling onto what looks like the nickel tail. The slope isn't always perfectly consistent. It's more just like instead of looking like this, it looks like that, kind of. And also, for observations, the data points really look more like this. The better the time sampling, the more you get. The time scales here, this is about 100 days. This is kind of a couple months or a month or so. This is a week. This is maybe a week or a couple weeks. Yeah.
So with two P's and two L's is the only, well, besides the hydrogen, is the only difference that you get this, because of the large radius, you get this initial spike compared to the other ones at shock breakout.
Between two P's and two L's? Or
Two P's and two L's versus the other ones. Like,
versus
you have
the other
that-
ones. Yeah, so no, the only, I will get into what the major difference is. The major difference is these do not have a lot of hydrogen or even have no hydrogen. These have hydrogen, and it turns out that actually the recombination of hydrogen will end up setting where your photosphere is.
What was the timescale for 2Ls again?
Similar on the kind of tens of days to 100, to 100 days. It depends on how bright, how long they last. You also have two peculiars, which are really 87A-like. They have similar timescales as the 2Ps. Their light curves look more like this with a broader second bump. And what this ends up telling you is you have a burst of light, but then there's a lot of hydrogen, but your radius is compact. So you actually start your plateau or this phase at lower luminosity, and then you pick up luminosity also as you deposit more heat from the nickel decay. I also won't talk too much about these. We also, the nice thing is we get to see occasionally the stars before they explode. These typically come from yellow supergiants or yellow hypergiants. These come from red supergiants in general. These come from usually blue supergiants in general, but these are often thought of as merger products or accretors or some weird way that you get a very compact star, even though physics wants to make you have a big puffy envelope. Yes,
Wait, the
Andrea.
2Ls are also RSGs?
I don't know.
Okay.
I think 2Ls are maybe RSGs, but part of the problem is there are tens of red supergiants seen before they explode. There's like a few 2Bs. The 2Ls are even intrinsically rarer, so I think that there are.
We haven't seen a progenitor.
We maybe have seen a progenitor, but we haven't seen that many. So it's hard to say at the population levels. There's also a bunch of questions of whether this early peak is caused by just a high explosion energy or if it's caused by interaction with circumstellar material. I'm going to table all of that, and we are going to now talk about what governs the light curve evolution, right? What are the physical ingredients? So actually, I'm going to cast this out to you for a moment and take a little break and make you interact with each other. I want you to spend a couple minutes thinking about it to yourself. What physical ingredients are going to govern the brightness, duration, the light curve evolution? Then I want you to turn to talk to the person next to you. If there's a group of three, you can talk in a little group of three. And then I'm going to ask the class to report. So we'll give it a couple minutes also because I am a little sick of hearing myself talk.
Just to follow up on what Andrea was asking, so there are 2 or 3 2Ls that have yellow supergiants, the giants.
I actually realized this is what I see in my simulations as soon as I said that. My very low mass envelopes look like 2Ls.
Right.
Yeah.
Okay.
That maybe isn't so surprising in that
Yeah.
It's really just. really short spike.
Like it's a continuous.
Oh, I forgot.
Yeah, I'm sorry.
Two ends. There's narrow lines. Narrow means there's interaction with slow-moving stuff. The light curves look like whatever. Some look like this. Some look like that. Some look like that.
Oh, like the duration.
It's great. Two ends are fun. Thank you very much. A lot of fun stuff with two ends.
This is like the way around, just more mass for the It turns out it's very hard
And I guess we would, if you're doing a free spike.
based on this picture. This is a progression. Well, and at times the explosion was so I'm just saying, like, this is
That's not necessarily. And this is gonna.
All right. Wrap up the sentence.
But that's why I'm speechless.
What did some of you think about succinctly? I'll take representatives from different groups.
Red herring, angular momentum, but we're not going to use that.
Red herring, angular momentum, but we're not going to use that. What other physics maybe sets?
We're deeply insulted, but we're gonna let it.
We'll
come.
talk about
That's
angular momentum
okay.
on Thursday.
Yeah, this
Whatever.
is angular momentum will be discussed more throughout this this school, but today we are not worrying too much about angular momentum. Other things. Yeah, in the back.
Yeah, we talk about the composition, like the hydrogen, will influence the recombination, and like CN and the nickel that will affect the vector, and also like how the size of the star, larger star will provide more energy.
So the size of the star, the nickel content, the so size is also both mass and radius, the energy of the explosion, the composition of the star in particular, whether there's hydrogen, and what you mentioned was also recombination. That's a pretty important piece of that puzzle. So let's get into that a little bit. So we have our ejecta that's expanding, and we can just ask, as this expands, well, it becomes easier and easier to see through. And here's why. Well, you have the density that's decreasing, but the radius is increasing. So your optical depth through the ejecta goes like your opacity times your density times this radius, or really kind of kappa rho r. Your density goes like m over r cubed. So this goes something like kappa m over r squared. Okay, so as if you have more mass in the ejecta, it's more optically thick. If you have less mass in the ejecta, or sorry, if you have a bigger radius, it actually ends up being easier to see through. We can also, right, so as R goes up, the opacity goes down, right? And in general, you're going to radiate heat from the photosphere of this star roughly where tau equals 1. But the heat is sourced deeper in. And you can ask, when do photons start to get out? Well, you have a race between a photon, which is kind of trying to do a random walk diffusion process out of this expanding ejecta. And you also have the ejecta that's expanding. The radius of the ejecta can be described more or less as r equals r naught plus dt once there's no acceleration. You can ask, when is r naught small? It's after a few expansion times, and in most of the supernova's evolution, are not as small, so R can be written as more or less VT. I'll come back to that as well. So you can ask, well, when is the expansion time R over, when is the expansion time equal to the time it takes photons to diffuse out? You can similarly cast this as when is the expansion velocity V equal to the diffusion velocity, which is the speed of light divided by the optical depth. So this is where is the luminosity sourced? It's sourced at the location where tau is C over V. That is, the photons are trying to escape out faster than the ejecta can expand. This also determines the condition for shock breakout, where this is when can the first photons ahead of the shock escape faster than the shock is propagating out of the star. In that case, it's using the shock velocity rather than kind of the expansion velocity here, which is just the velocity of my one zone model. All this ball is expanding.
So why do I care about tau equals 1?
You care about tau equals 1 because the photons are still scattering and diffusing. So somewhere along this path, you thermalize with the ejecta. So if you care about the observed temperature, or if you're an observer hoping to look in optical bands, this material does still matter to some extent.
Somewhere between tau
Yes.
equals 1 and tau equals 0.
Somewhere between tau equals 1 and tau equals
And
C
kappa is
over V.
electron scattering.
And right now we're writing down kappa as electron scattering. Right? Now we can also heat the ejecta. We can heat this with nickel decay. We can heat it with the explosion itself. I'm going to do the pure explosion in a second. We can heat it with a central engine like a magnetar or circumstellar interaction that Brian drew with a disk that sort of wraps around the disk. You have an interaction here. We can also heat it with, I said nickel decay. We can also heat it with circumstellar interaction at the very surface. That's fine. So an important question, though, because your optical depth is sensitive to the opacity, is what is setting that opacity? And in the high energy explosions, it is typically assumed that most of the opacity is set by electron scattering. All right. I'll come back to that in a second, but first, so now we can think about what sets the luminosity overall. Overall, the luminosity is set. Luminosity is energy over time. What energy? Well, this is the energy in radiation. What time? Well, this is the diffusion time, the time it takes the radiation to escape. I'm going to call this ER, I'm going to call this T supernova for my characteristic time scale of a supernova. My energy in radiation is the volume, r cubed, or 4/3 pi r cubed, times the energy density, which for radiation-dominated explosion is AT to the 4th. Again, I'm doing a very crude one-zone model to build intuition for how these things scale. Well, what is T supernova? We can go back to this scattering process and write down a diffusion timescale that is something like the number of scatterings times the mean free path over the speed of light is something like, for a mean free path that is 1 over the number density times the cross section, which is also equal to 1 over the opacity times the mass density. The number of scatterings from root n statistics, you have to take sort of the square of the number of scatterings in order to travel, in order to get your mean free paths to end up getting out over some distance r, this ends up going like r squared over lambda, which is the value you're trying to cross. This is just converting, and sigma goes like r over lambda squared times 1 over c, which gives you, plugging in now for lambda, we get kappa, the opacity, times the density, times r squared over c goes something like kappa m over cr. But my radius here is changing. And in this one zone model, we've written down that r goes like vt. You can actually ask, when does this become equivalent? 1,000 solar radii, which is your initial radius, is something like 10 to the 14 centimeters. 10,000 kilometers per second is something like 10 to the 9 centimeters per second. So your time becomes like 10 to the 5 seconds, which is a day or so. So after the first couple days of the supernova, at least in the outer layers, this more strict condition of homology is what it's called, is satisfied. So I'm going to now replace a lot of r's with vt's. Moreover, so I'm going to write this here, r equals vt. Moreover, as the r is vt. Moreover, as the ejecta expands, the radius increases, adiabatic losses occur because you were trying to do PDV work. You expand this ejecta, the temperature drops. Specifically for a radiation, in general, we can write down an equation of state for an adiabatic expansion. We assume that the radiation is not carrying too much of the heat out. We get that P goes like rho to the gamma. This is for an adiabatic equation of state. For radiation-dominated plasmas, gamma is 4/3. So P goes like AT to the 4th, goes like rho to the 4/3, goes like M over R cubed to the 4/3. So you end up getting that T goes like 1 over R. Or 1 over time, because R goes like 1 over VT, or R goes like VT. So now we're going to plug this equation. We'll write down that the temperature equals my initial temperature from the explosion times R naught over R, where R naught is the initial radius. We plug this in to this here, and we get that the luminosity goes like R, well, the luminosity goes like A T naught to the 4th, R naught over R to the 4th, times C. Well, we'll now divide by this, right? So we'll get R C over M kappa, and then we'll multiply by the volume, 4/3. I'm just going to call that R cubed. We get R to the 4th, we get R to the 4th. A nice thing is that these initial radii cancel. Right, so we get the luminosity, we get a characteristic luminosity scale that I have to write down here so I don't pass this line. It was something like my initial radius, A C T naught to the 4th over kappa M, which ends up, if you say AT to the 4th, is your explosion energy. I'm missing something, but
With the R cube. It's
With
the
R
explosion.
cube.
Yeah, right, with our, right, with R cubed. Yes, right, perfect. So with R cubed, it's the explosion energy, so you get something that looks like the explosion energy times the initial radius over the opacity times the mass. And this is the result that Brian showed yesterday. So, more energy, you're brighter. Bigger initial radius, you're brighter. More mass, you're actually fainter, in part because you're distributing the energy over more stuff. So every bit of stuff is not quite as hot, and it's not moving quite as fast.
This is the ejecta mass.
And this is the ejecta mass, or the envelope mass. I'm kind of using a mass scale in all of its one-zone model. But yeah, this is more or less the ejecta mass. And again, we can write down the duration. Well, we have this kappa times the mass over the radius. We can ask, when is this diffusion, right? Because this number is changing as the radius changes. We can ask, when does the diffusion time equal the expansion time? So,
Well, isn't that student to get tau equals C over V?
Yes. Let me just recast this for a sec. I'm going to put my R explicitly in terms of VT. I'm going to put my T upstairs. Right, so now I have a T squared goes like this. So then my time, my duration, T squared goes like kappa times the mass over C. This explosion velocity goes something like the square root of E over M. 1/2 mv squared is explosion energy in this very crude one-zone model. So now we find that the duration goes something like e to the minus 1/4 m to the times the mass to the 3/4, again with an opacity dependence.
Is the energy radiative energy?
So the explosion energy at roughly the initial shock breakout is split kind of half in radiation, half in kinetic energy. So it's we're saying E supernova is everything. Actually, asymptotically, that explosion energy mostly goes into the kinetic energy of the ejecta. Only a small fraction of the total energy in these strong explosions ends up being radiated away because the stuff expands pretty quickly, and so the energy degrades. The internal energy degrades pretty quickly. Okay.
So
Yeah.
why does that go to luminosity? It's not radiative energy.
The initial radiative energy, right, R cubed AT initial to the 4th, is proportional to the explosion energy. There's a factor of 2, maybe,
Okay.
but the initial explosion energy does determine the initial energy in radiation, and that's what's encoded in this R naught and T naught term.
So it's just in the twiddle.
It's in the, yeah, why this is the supernova energy is a little bit in the twiddle. But you can do it more rigorously, assume equipartition, and then you can make the twiddle an equals 1/2 and then put your 4/3 pi back in and all of that stuff. Yeah. And again, this is a one-zone model. This is very simplified. But we can go back and refine this whole picture. Because the entire thing is not an expanding sphere, and there's some sensitivity to this opacity, which maybe isn't quite so simple, because as the ejecta expands and cools down, eventually your temperature gets cool enough in some of the layers of this ejecta that hydrogen recombines, and all of a sudden you have ionized hydrogen and then you have neutral hydrogen. It's really easy for photons to get through neutral hydrogen. So instead, your opacity looks like a step function where you have ionized hydrogen on one side and neutral hydrogen on the other. And that's determined by the temperature where hydrogen recombines. Similarly, because T goes like 1 over R for this adiabatic expansion, if we end up fixing the temperature of where the photosphere is, we are similarly kind of fixing the radius of where the photosphere is. So we can imagine this expanding ejecta that is passing through some radius. And as it expands, your radius coordinate is your temperature coordinate, gets set at roughly the ionization or recombination temperature of hydrogen. And this becomes the surface that you see, because as your ejecta gets cooler than that, you see through it instantly. And when it's hotter than that, you don't. So I'm going to refine my picture a little bit. I'm going to now write down, so if my luminosity goes like E over T supernova, and E is R cubed, a T to the 4th, and T goes like 1 over R, and then R is VT. You can write this as also my energy goes like my initial energy with adiabatic losses, or my energy is E naught times some initial time scale over T. Plug all this back in, and really we have a nice equation that goes like the initial or explosion energy times my initial expansion time scale, R over V naught, initial radius over the kind of initial ejecta velocity. And then we'll do this over T supernova times T supernova. Which ends up being T supernova squared, my diffusion time squared. Now, if you plugged in your T naught is R over V, and your T supernova squared is kappa M over V naught, you reproduce what's above. Yeah.
What is T naught?
T naught is my characteristic initial expansion timescale. I'm defining it as the radius of the star initially divided by the shock velocity, more or less, which goes like ρd over. It's kind of the characteristic initial expansion timescale initially. Right, you reproduce the scalings, but this expression for the luminosity is more generic. This can help us in a moment, right? I mentioned that the ejecta is hydrogen rich, which means the opacity shouldn't be taken to a constant once the temperature drops below 6,000 Kelvin. Now you can write down similar scalings for recombination only. We can equate this to the fact that the luminosity is 4 pi r squared sigma T to the 4th up to some dilution factor that's really just proportional to the luminosity. I know how to write a nice psi, but I always write them as squiggles because I don't believe them. Yeah.
Just to clarify, so what is E?
This is my explosion energy.
Oh, so
Or my
what's
initial.
the difference between E and E subscript Sn?
So my E, I like when I try to write E or ER, I'm a little fast and loose. I mean, at a given time, how much energy is there in internal energy? The ESN or E naught is just ESN, is the explosion energy of the supernova, the total energy that I dump in, which is proportional to the initial energy in radiation.
So why
By
do
a
you
factor
have
of 2.
that the energy is increased, like it's like linear, right?
Oh,
Oh.
why does the energy change? So
Yeah.
the energy,
Dependence on time, yes.
yeah, has a time dependence. As you expand, you have less internal energy left because some of your internal energy has been translated to do PDV work to cause, to sustain this expansion.
I see on it.
It's adiabatic losses in energy because you have the medium expanding. Yeah, John.
Just while we're asking
Yeah.
term definitions.
Please.
You call this a one zone model.
Yeah.
What would not be a one zone model? What about this is one zoning?
So what was one zoni was I'm calling everything the same, a mass, a radius, a velocity, and everything. You can do the same calculation for individual shells. You'll see something like that a little bit later in this week. You can also do it, what I'm going to show you now is sort of a two-zone model where we have optically thin ejecta and optically thick ejecta, because we have stuff that is ionized and stuff that is not ionized. And that's basically a two-zone model. Okay, so you can write down scalings when you kind of plug these in for recombination only, that this is the ionization temperature is 6,000 Kelvin. And R goes like V T supernova. Let's skip that. Instead, we're going to take into account both recombination and diffusion in our picture. But I'm going to keep that up there for a second. So I'm going to define the photosphere radius with this blackbody equation. I'm going to say that my photosphere radius is, so if L is 4 pi r squared sigma t to the fourth, R goes like L plateau over 4 pi sigma t to the fourth, where this T is the ionization temperature of hydrogen, or the recombination temperature, roughly 6,000 Kelvin. Now, if we plug this back in here, where we have swapped, well, we take this equation for the luminosity, plug it in up here. My photosphere radius goes like E naught T naught over T squared, 1 over 4 pi sigma times the ionization temperature. We now,
The fourth.
yes, the fourth, right? We can plug this back in to our equation for, here, I'll write it down again. We can plug this back in. My T supernova goes like kappa times the mass over C R, or LP is, yeah, L plateau or L photosphere. It's L. When we identify the supernova luminosity as this plateau luminosity. You plug things back in, you end up getting that my supernova time scale is this R squared. So I have my M over R. I'm going to make this M over R cubed R squared, because then this gets me a density, which is nice. So I have this, I multiply, I plug this in for R squared, and I also plug it in here. We remember also that T naught is R naught over V naught. We also remember that V goes like root E over M. When you plug it all in, you end up finding that T goes like I'll do it E naught T naught over T. We're going to have to do some multiplication. Squared 1 over 4 pi, or 1 over 4 pi sigma T to the fourth, kappa M over CR cubed, where this R is also the square root of this whole thing, E naught T naught over T supernova 1 over 4 pi sigma T to the fourth cubed. Put it all together, the duration then goes like e to the minus 1/6, the ejecta mass also to the minus, or to the 1/2, radius to the 1/6. We've introduced a radius dependence. We also have the opacity to the 1/6 and the ionization temperature to the minus 2/3. Plug this back into my luminosity equation. We get e to the 5/6, ejecta mass to the minus 1/2, initial radius to the 2/3, another dependence on the opacity to the minus 1/3 power, the ionization temperature to the 4/3 power. And these here are the scalings of Popov 1993. Which was the first paper I had to read during my first project for my PhD, and it's a lot of math. And you can get to these scalings with physical arguments. I went through this. If you want a good reference for deriving these in a more intuitive way, I highly recommend Kaysen and Woosley, Dan Kaysen and Stan Woosley, 2009. Okay, so we now have new equations for the luminosity and duration. Note that still we have a dependence on the energy, that's more energy, brighter explosion. We have dependence on the mass, that's more mass, fainter explosion, and a dependence on the radius, that's bigger radius, brighter explosion. That qualitative picture doesn't really change that much. So people, in fact, you later today, will fit the initial Arnett-like diffusion model to light curves. You will find something that is kind of right. This is also only kind of right because we've treated the ejecta as two zones and we've treated the opacity as a step function of infinity 0, basically, at the ionization temperature.
No, not infinity.
Not infinity. You still have the kappa in there, so it's the scattering opacity, not infinity, but yeah.
0.4.
0.4-ish. 0.4 is infinity compared to 0. Okay, so there were a few more points I wanted to make. You can also write down, and I won't derive it here, you can write down an extension to this from nickel decay. The way you do it is you say, my internal energy is no longer just my energy in radiation, but you expand this to include the decay energy from nickel and from cobalt, in which case you basically have a correction that's 1 plus something times the mass of the nickel times your internal energy. You run through the math, you end up getting a new scaling for the plateau duration that instead the radii scalings actually end up canceling out. In the nickel-rich limit, you get that the plateau duration looks more like the nickel mass to a power times the ejecta mass kind of to the 1/2, but it's actually the 5/12, and the explosion energy to the minus 1/4 instead of minus 1/6. But again, all of this is sort of scalings with similar qualitative character.
How much nickel do you need to get into that nickel-rich limit? Like,
you can actually write this down. I would say it's something like about the mass of nickel in a typical 2p. So nickel, it's something like 0.03 to 0.04 solar masses, which is about the amount of nickel in a typical 2p. All right. about 10 minutes, there is one more thing that I really want to get to, so I'll do that. We now have 2 equations and 3 unknowns. We have the mass, energy, and radius as unknowns, and we have the brightness and duration as our observables. The nickel mass folds into the duration equation if you go in the nickel-rich limit. Or if you don't, then it's still an equation, it's just not a linear one. Linear algebra tells us that if you have 2 equations and 3 unknowns, you get constraints, but not a unique solution. A lot of people really want another thing that helps close that system of equations. One of the, I was going to throw this out to you, but for the sake of time, one of the more promising things is that we actually do see the ejecta expanding, and we can measure roughly the velocity of that expanding ejecta. For reasons I will explain, that doesn't end up closing the degeneracy. However, it is a nice, useful, interesting result. So I think it's worth saying. But first, what do observers measure when they measure a velocity? You now have a photosphere inside some ejecta. This is expanding. And let's say your line is forming just outside your photosphere. Now we're doing the Doppler shift of a line. We have a photosphere shining through it. I'm going to put my observer here. I'm going to draw my line. Here's my line center. I'll also note that you can't see anything behind the photosphere. The material along the line of sight absorbs. You have an absorbing column here that's blue shifted. Here, you actually get some amount that's emitted and some amount that's absorbed on your way to you. If this is all moving towards your line of sight and this is moving away from your line of sight, this is blue, this is red, you end up getting an emission feature at line center. This is called a P Cygni profile. This line profile appears in P Cygnus, which is a very windy star, and you can, from the Doppler shift here, measure more or less the characteristic velocity coming towards you. So this gives you, more or less, the velocity of the supernova. It's sensitive to where the line is being formed. If your line is formed farther out or deeper in, then this will shift accordingly. So not every line needs to have the same velocity because they're formed in different regions of the ejecta. And your velocity profile in the ejecta does increase as you move outwards. I didn't derive that, but you can take my word for it. Also because if it went down, then this stuff would run into that stuff. The stuff inside would be running constantly into the stuff ahead. So you know, it's either flat or increasing, and in this case, it's more or less increasing. This is also sensitive to the abundance. Okay, so one might want to say, well, we'll measure a velocity. My explosion energy goes like 1/2 m ejecta b squared. The question, though, is what velocity are we measuring? And when does the velocity kind of match this 1/2 mv squared? We had 2 equations. This is a unique third equation, if it's right. But the trick is figuring out, is there a velocity or is there a time when this is true? Well, if we are probing the velocity during the plateau, unfortunately, this doesn't work. Because during the plateau, we'll go back to our 4 pi r squared sigma t to the 4th for homology, which is achieved after about a day or so. This goes like, this is the photosphere radius. This is the radius of my shell that I'm calling the photosphere at any given time, which is the velocity of that shell at any given time times the time. This is going to, so say we try and measure this velocity, because really this is more or less the velocity we're measuring. It's the photosphere velocity, the velocity of the photosphere shell, or the line closest to it. We get that this luminosity of time is 4 pi v squared sigma t to the fourth times, again, my little dilution factor, which is just proportional to L to some power. Rearrange, and that my velocity goes like root L over time. At fixed time, up to some fudge factor. So at some time, some other fudge factor. At fixed time, then, this is a standard candle. So this standard candle was even observed in 2002, and people are using this for an alternate cosmology. This is a rehashing of what's called the expanding photosphere method, which has been known for a very long time. Unfortunately, it means that we can't simply use the velocity evolution from the plateau onward to constrain anything in addition to the luminosity. It does mean that we can do cosmology. So if I were to make a plot of all of the supernovae that we see, and I plot their luminosity and their velocity, I can draw a theory relation from the photosphere that goes like L goes like V squared, or it's more like 2 point something or 1.9 something. We then have sort of a spread above that from where the iron line or other lines you're looking at are actually formed. This is controlled by another optical depth term called the Sobolev optical depth. We don't need to get into that, but it's just sort of where is the line being formed, which is slightly farther out than the photosphere. So it's at slightly higher velocities for fixed photosphere. Observations usually fall somewhere in this region. Every so often, there will be something down here. Well, that's weird. Why might it be weird? Well, it means you have luminosity in excess of your velocity. One way you can do that is with an additional heating source that is then immediately radiating away. So circumstellar material will not often, but circumstellar material can make something overluminous, but also even suppress the velocity. So that can kind of push you down here. If you have something way up here, it means it's moving very fast, but the luminosity looks low. One way is that maybe the luminosity is coming out in bands you aren't observing, etc. That was fun. I can get into early times, but I think this, for broad strokes, for core collapse, can be where we leave off. I will make my notes available. Thank you all for your time.
I think we've had a really interactive session, so that's great. Any quick 1 or 2 questions before we head out to coffee break?
So you said that the emission lines that you're getting P Cygni profiles from are coming from different depths. So presumably the opacity is going to be lower for more infrared lines. So can we, in this model, can we expect an ordering of, like, if I see this P Cygni profile on this line, can I expect a different, some scaling to a redder or a bluer line?
I want the answer to be yes. And I expect yes. I don't think there is a lot of theory work showing what that scaling or what that relationship should be. It involves a little bit the self-similarity of the velocity profile in the ejecta. But I do imagine that with an understanding of also the abundance ratio, if you have a lot of iron versus less iron, but the hydrogen is more or less the same, those may be formed at different depths, but they will probe different parts of the velocity profile. I do think that those differences are interesting because the overall ejecta profile does go like 1/2 mv squared as the explosion energy at fixed mass coordinate. It's just that you're seeing deeper and deeper and deeper in, and the photosphere sets the velocity that you see. So if you can probe multiple points on this, you actually could, in theory, use that to break this degeneracy. Other alternatives are the fastest moving ejecta at the very early times does more or less, if you know you're looking at the outermost mass coordinates, that also behaves more like 1/2 mv squared as the explosion energy. When your temperature is not set by recombination or ionization, at the early times when you're hotter, then you don't have to, then you can actually make use of that information a little bit more. The problem is that epoch is very sensitive to other things like interaction with the stuff around the star, which is becoming a very hot topic or cool topic in supernova science these days.
So can you break the constraint from like radio observations to have like the expansion to have the observation?
Potentially, yeah. Another promising one is you can look at like line ratios in nebular spectra that give you some sense of the core mass and thereby initial luminosity. If you assume something about the initial temperature, that can also give you the initial radius. One thing I wanted to get into but couldn't was that in the shock breakout in the first flash, basically, yes, anything that helps you measure the radius of the star, you have the mass, radius, and energy, and 2 equations, 3 unknowns. If you can probe at either the mass or radius or energy or some linear combination of them in a scaling that isn't the scalings that already exist for the brightness and duration, any information from that can help close this loop. One way you can also do it is shock breakout. That's one that I wanted to get into, but roughly the duration of the shock breakout is set by the light. Well, it's set by the crossing time of whatever. Well, the duration of the shock breakout is either set by the diffusion time out of the outer area, or the light crossing time of the total ejecta, or some geometric factor for obliquity or lumpiness, which is the time it takes the shock to cross the inhomogeneous layers. Whichever of those is the longest time scale will smear out the shock breakout the most. What that means is if the light crossing time is the correct answer, then for T light crossing, that goes like R over C. If you measure the duration of your breakout pulse and you can identify that the light crossing time is the longest time scale in question, then you can get a direct constraint on the radius. But I, for many reasons, don't really believe that this happens in most core collapse events that are in extended progenitors. I think in red supergiants, light crossing time is basically never the key because their envelopes are way too lumpy and way too inflated. So either you'll get a longer diffusion time or you will get a longer geometric time in typical red supergiant explosions.
All right, we will start our second lecture for the day. This lecture is going to be by Anna Ho. Anna did her undergrad at MIT and was a grad student at Caltech, and she went on to postdoc at Berkeley, and then after that has been a professor at Cornell. Anna works on the most energetic transients, the fastest, the brightest, the most luminous stuff, and today's topic is going to be about the observational diversity of massive star explosions. Oh,
Sorry.
Thank you. Also, just a quick reminder, please use the microphone when asking questions because we'd like to record the interactions that are happening.
It's this.
Is it on? It should be green.
Hello?
Yes. Yeah, perfect.
Okay, is this on?
Yes.
Okay, excellent. Just a moment. Okay, Good morning, everyone. Very nice to meet you and also very nice to see some familiar faces. As Kishole said, I'm going to be talking about the observational diversity of core collapse supernovae. I think you got a sort of theoretical overview from Jared this morning, so I think that'll set the stage nicely for what we'll discuss now. Before I launch into this, I'm just curious to get to know the group a little bit since there are many faces that are new to me. So is there anyone here who is in their very first year of graduate school? Okay, just a couple of people. Is anyone doing their PhD on core collapse supernovae? Okay, a few people. So what are you focusing on?
CBLs.
Okay, 1C broadline supernovae. What about you?
Magnetars.
Magnetars. Okay, so these are all kind of extreme events. Any sort of type 2Ps? Yes. Okay, great. What about other stripped envelope, 1B, 1C supernovae? Yes. Okay, I think we've pretty much spanned. Oh, what about interacting supernovae? Yeah, great. Oh, excellent. Okay, great. All right, so I think we've covered most of the observational diversity in this room. It sounds like there's a lot of expertise here already. Okay, so I'm going to just do a very high-level summary first. And so I'm sure, as most of you know, when I say core collapse supernova, we're talking about the death of a star that's more massive than around 8 solar masses. These are, relatively speaking, common. They're kind of the most common type of cosmic explosion that we have. The rough rate, a useful number to bear in mind, is about 1 in the universe per second. And roughly 1 in a galaxy per century. Why do we study these events? They are the origin of many of the elements, including the ones important for us, carbon, nitrogen, oxygen. They are the dominant source of momentum and momentum to galaxies. These are incredibly energetic events. And so to understand the evolution of entire galaxies, you really have to understand supernovae. And then, of course, there's a lot of interest, particularly now that we have gravitational wave detectors and understanding the origin of compact objects like neutron stars and black holes, and being able to explain their population properties, for example, their mass distribution. And to do that, we really, again, need to understand supernovae. So what are we trying to do? I would say that the overarching goal of this field is to construct a complete mapping from the properties of the star as it is, say, on the zero-age main sequence, to what its structure is immediately prior to the explosion, to the properties of the supernovae themselves, which in some cases we get things that don't even look like what we know of supernovae. You can get all kinds of weird transients. And then all the way to their compact object remnants. And for for a long time, the standard story was that the dominant determinant of all of this is the mass of the star. But today, what's really happened in this field in the last decade or so is that we've been forced to confront the reality that there are poorly understood processes, mass loss, binary interaction, that really play a deterministic role in this whole story. And we are finally being forced to confront that because of what's being found in wide field surveys, because of some strange kinds of transients, because of developments in theory and modeling. And so I would say trying to incorporate all of that into retelling this complete story. If we could do that, we would be done. No problem. Okay, so what are some of the?
What are the extra things that matter? So
Yep.
It's obviously the mass of the star.
Yes. Yeah.
Winds may depend on the mass of the star.
Yep.
So the other things may be metallicity.
Yep. Absolutely.
Rotation.
Yep. Absolutely. Yeah, I'll list some of those here. Thank you. Yep. Say multiplicity. When I just wrote mass loss, we've learned that this is not just steady winds. So massive stars all have some kind of steady wind. But for example, in observations, one of the big developments has been the recognition that a very large fraction of supernovae undergo some kind of very enhanced mass loss in the days to centuries prior to the explosion. So orders of magnitude greater mass loss rates than you would nominally expect from a stellar wind. And so trying to incorporate that into our story is one of the big things that people are trying to do in this field. All right, some observational frontiers. There are many, and I definitely can't do justice to them today. I'm going to focus on a couple. One is making the discovery more systematic. So doing something more like a census of core collapse supernovae in the universe. Before it was a bit more just haphazard individual object discoveries. And then another is, if I write down here, oh no, there's no way you can see. Okay. Rapid response. So discovering events when they are very, very young. And the younger they are when you start observing them, the closer you're really getting to the properties of the progenitor at the time of explosion. So from doing a census, you get, of course, rates, but then you also more readily recognize unusual types of objects. From rapid response, as I mentioned, you get closer to the properties of the progenitors. There's also some sort of interesting physics here. For example, in the shock breakout at the very onset of the explosion. And like I said, there are many others as well. These are just two that I think are particularly relevant since this is an LSST summer school, but people observe core collapse supernovae in basically every part of the electromagnetic spectrum. So speaking of that, actually, let me just calibrate what can people see this last line? No. Okay.
You can see it on the screen.
Oh, interesting. Okay. What's the end that you can see? Like here?
Here?
Goal.
Yeah, here. Okay, let me I'll bear that in mind. Thank you. All right, so what does a core collapse supernova actually look like? Sometimes when I talk to members of the public and they ask what I do and I'm trying to explain, they always ask me how fast a supernova is. And so then I have to explain that there's how long it actually takes physically to happen, but then there's how long the emission lasts. And those are kind of very different things. So I'm going to go through the sort of basic stages that I think you've already heard about. Right, so of course, initially you have the core collapse, only takes about a second. From that, you get gravitational waves, and you get a burst of neutrinos. These are lasting maybe seconds. This was seen famously in supernova 1987A, which was in the Magellanic Clouds, so very satellite galaxy of the Milky Way. Then so initially, you don't see anything from photons because it takes time for the photons to diffuse out of the supernova ejecta. But eventually they are able to escape. And that moment is the shock breakout. And the length of this depends on the progenitor. I'm going to say maybe hours. You might see a burst of X-rays. Maybe you see a burst of UV if your progenitor is very large. All right, so now the photons, the sort of initial photons have escaped. As the shock ran through the star, it heated up the material and synthesized radioactive isotopes, the most common of which is nickel-56. And then the optical light curve is really governed by the radioactive decay timescale. Optical. And for the most part, when we discover core collapse supernovae today, numerically, our discovery rates are dominated by surveys operating in the optical band. So most of the time when we discover a core collapse supernova, this is the step that we're actually seeing. And then finally, so that's from the sort of hot and cooling, the hot gas, the radioactively decaying material. And then you have an explosion. So all this ejecta has gone out into space. There's dust and gas there. Some of it was made by the progenitor itself. Some of it was there, just is sort of interstellar material. And you can have, so the ejecta collides with that material. And we typically study that as radio emission, X-ray emission, commonly synchrotron radiation, and that goes on for years and years. And the duration is really just set by the sensitivity of our telescopes. Okay, so this is just a very broad overview. I'm now going to talk a little bit more specifically about how we actually classify events and talk about some of the peculiar types of events that we've been seeing. Before I get into that, I'm happy to take any questions. Yes.
Just a quick question. So you said that for shock breakout phase, it's going to be in UV if the source is really big. Do you mind explaining why?
Oh, sure. Yeah. So the right. So the question was about the duration of the duration and the wavelength of the shock breakout event. It just has to do with it's basically, you can think of it like black body radiation. And so if the source is larger, the temperature is going to be cooler. And so the peak is going to be at longer wavelengths, roughly. Yeah. Any other questions? Okay. We'll talk about classification. Has anyone here done spectroscopic classification typing of core collapse supernovae? SNID? Yeah. Okay, so how is this done? When we classify core collapse supernovae, this is typically done on the basis of their optical spectra. And so I have the classification scheme shown in the back. Sorry to make you turn around. There won't be a large amount of slides, so I'll only ask you to do this a few times. So there's essentially a sequence of most hydrogen-rich to depleted in hydrogen and then depleted also in helium, and that's how we've been classifying supernovae for many decades. All right, so what are the types? Two main types. Type 1 is no hydrogen. So type 1 supernovae mean no hydrogen, type 2 mean that they have hydrogen, but then there are lots of subtypes, as you can start to see in the figure there. One kind of caveat is that it's most common to classify around peak brightness. And by that, I mean, if the light curve looks this, then people are often doing the spectroscopic classification when it's brightest, just because that's when it's easiest to actually do the spectroscopic classification. But there has been a lot of work showing that classification can be time dependent. So if you classify here versus you classify 2 weeks later, you might get a different type of supernova. And so one of the objects that I'm showing on the right hand of the slide there is something that you would have said, oh, that's a type 1c supernova based on the spectrum close to peak brightness. But then much later, it became classified as a type 2n supernova. So that's makes this a little bit more complicated, and I'll say more about that a little bit later. Okay, I think we're starting to get to where people can't see what I'm doing. So over. Or maybe I'll just erase this. All right. So I'll say, give a little more detail on these two different types. So type 2s. These are very heterogeneous. So their optical light curves and optical spectra can show a wide range of properties. Okay, there you go. There are, when we're subtyping type 2s, people typically do it by the morphology of the light curve or by properties of the spectra. So I'm first going to write the types that are based on their light curve. That's the 2 Ls, the 2 Ps, so 2 Ls, 2 Ps, and 1987A like, meaning they're similar to this famous supernova called 1987A. Those classifications are done based are basically describing the shape of the optical light curve. And then there are some based on the spectra. Bs, so the 2Bs and the 2Ns, these are classifications based on spectroscopy. So 2B means that you are a sort of transition object between a type 2, so hydrogen rich, and a 1B, which means hydrogen poor. So they're sort of weak hydrogen lines. And then 2N, the N stands for narrow. And it means that here you're seeing hydrogen because it's a type 2, but rather than be in absorption, as is typical for supernovae, the lines are actually in emission, and they're much more narrow than the typical absorption lines that you have. Okay, so on the back now, I have a plot showing the light curves on the left, and those are just the types, some of the types that I've listed here. So the linear decline, so wait, 2 L's linear decline, the 2P refers to a plateau, and then the bottom one in kind of red, you see there's a very long rise, and that's this 1987A like. type of event.
Question.
Yes.
Do the two Bs become one Bs in their spectra at late time?
Yeah, so that's a good question. 2Bs also have a lot of diversity. So some of them, it can be tricky to say 2B, 1B, and then it can depend, which one you would conclude might depend on when you are classifying it. But even at late time, some of them can have a fairly distinctive spectrum that's still different from a standard 1B. So it's hard to give a single answer. It depends on the object. Yeah.
I'm a little bit confused. So for instance, if I take one supernova, I look at the light curve, I classify with the light curve, and then I look at spectrum and I classify with that. Then would it be just like, is it like a distinct way to classify, as in like saying that like 2N is not, can it be like 2L at the same time, or how does it work?
Yeah, that's a great question. And again, it depends a little bit. 2Ns typically have light curves that are different. So you might have a good guess that this is what it is based on the light curve, but ultimately to actually classify it, you need a spectrum. Whereas, you know, a 2P, that has a very, very distinctive light curve. And so you could be pretty sure that that's what it is based on the light curve. 2Bs, their light curves are, I would say it would be very difficult to classify them as that based just on their light curve. So you would need a spectrum. So there's sort of a, you really, the ground truth for classification in supernova studies today is based on spectroscopy. You ultimately need a spectrum to really say, if we're gonna actually report a classification of a supernova, that today is pretty much always based on spectroscopy. But there are certain classes that have distinct enough light curves where you could probably make a very good guess before you actually get a spectrum. Does that make sense? Oop. Any other questions? Yes.
All right, so if you could go back to this slide with the supernova that changed classification.
Yeah.
So first it's classified as a 1C, but I feel like maybe I'm making them up, but I already feel like I see the helium emission lines that would make it a 2N, like the narrow lines. I feel like the spikes are already there.
Yes.
So is this due to like limitations in the bank of templates that's used for classification, or is there?
Yeah.
Is it more important to see that silicon broad feature than the helium, or could something else explain those spikes? And I don't know, just why, if you know, why is it classified first? It was a 1C.
Yes. Yeah, that's a good question. So to my eye, so I agree. So, okay, first of all, taking a step back. So, right. So type 2N, narrow emission lines of hydrogen. So this prominent feature here is H alpha. So that's the hydrogen emission line. If you look at 27 days, that spectrum, it's sort of hard to really, I don't know how easy it is to see, but that's where the classification, you can see these very broad features. So this underlying shape, that's what's giving it the classification as a type 1C. And I think maybe what's a bit confusing is that you see prominent hydrogen throughout, but to my eye early on, it's much more narrow. So it's almost a single, you can barely really resolve it, whereas later you see that it actually has a width. And so actually early on, the thing that's tricky here is I think you're getting H alpha from the galaxy. And so you have a very, very narrow line that's actually from the galaxy. So the stars and the explosion happened in some star forming region or in a star forming galaxy. So you have H alpha from that. But then once you get a little bit later, you see it starts to get much broader. And that can't be from the galaxy. So that's now from, that is a supernova line. And so that's why early on you actually wouldn't have known that it was a 2-1. I think this is showing a galaxy line. So I think that's why it's a bit confusing. Yeah. Oh yeah.
Is a change like that considered very common? Just the one that you have as an example, or if I were to go classify a bunch of things at peak and then go reclassify a bunch of them, how many would I expect to change?
Yeah, I don't think we have a good handle on the rates of that, because to follow a supernova late, it would have to be pretty nearby and pretty bright. And currently that's not really done in such a systematic way. So it's still considered rare and noteworthy to see that, but exactly how common it would actually be, I think, is not so clear. Yeah, I don't know this specific event. I don't know much more about it other than that this classification type changed. But if you, there are single object papers that will report an event because it really transitioned from one to another. There was a big study led by Mariam Mojaz, who she's the one also who these figures came from. And she looked at trying to make a recommendation for when to try and spectroscopically classify supernovae. And their conclusion was about 2 weeks after peak light is sort of when you get the most useful information, rather than peak light, which is when most of us have been doing it. But I would say actually having really detailed spectral series for a large number of supernovae is itself still quite rare. Anyone want to add to that who studies core collapse supernovae? You're kind of nodding along, Sam.
I think there are like a dozen or so type changing in the literature. So, but like you said, it's like we don't have spectral series for a lot of these. So it's like, oh yeah, we have a dozen of them, but we don't have a good sense of the rates.
Right.
So I would say they're rare, but maybe that's an observational bias.
Yeah, agree. Yeah.
Yeah, I was gonna say, I think there was a paper by Rothmar Goody where she looked in the radio and X-rays and found like 10% of these triple envelope ones transition to two ends, like interacting with something at late times, but it was still limited by like how many have been observed and how many have they gotten in the radio and stuff.
Right. Yeah, that's a good point. You can also look for this kind of change at other wavelengths, because the same reason you get this hydrogen line start to appear, that same thing can also get you luminous radio emission, and so you could also search that way. And so Raphael, is that what's Raphael? Yeah, that's the name. Yeah, Raphael. I thought I recognized you. Yeah, Raphael's saying they've done studies of cross-matching optical supernovae with radio surveys, and they actually find a fairly substantial fraction of them light up. But maybe if you just waited for longer, you would see it in more of them. So yeah, we don't really have good statistics. Any other questions?
So maybe a clarification question, like the one we have behind. If I just look at the light curve, every supernova will fall on these three? No. Right?
No. So we're not every. So this is just type 2s for now. So I think so to me, these are the 5 type 2 subtypes. And so 3 of them do have fairly distinctive, in particular, these two, the 2 L's and the 2 P's, do have fairly distinctive light curves. But I'd say these other ones are, especially these 2, have fairly heterogeneous light curves.
Fine. So if I look just on light curve, I should have like a 4th line, which is sort of a generic, non-distinct.
Yes, sure. Yep. Yeah, absolutely. Yeah. Yeah. So there's other, I don't know. Yeah. So. Yeah. And in general, the 2 N's will be slower than the 2 B's. But it would still be, they have enough heterogeneity that it would be hard to classify based on just the light curves. Yeah. And also, you're starting to get into overlap too with the stripped envelope supernovae, which we'll talk about next. Yeah.
So the duration of the plateau in a 2B is like 100 days. So if you do observe like the peak spectra, do you know it's a 2P even without seeing the plateau in the light curve?
Yeah, let's see. 2Ps I think do have fairly distinct spectra. I don't actually know.
Okay.
I don't know if you could distinguish this based on the spectra. Does anyone know?
The P and L?
Yeah.
No.
You can't. Okay. All right, then. Yeah.
P and L look the same.
Okay. Okay. Yeah. Okay. Yeah. Thank you. I wasn't sure. Yeah.
Sorry, I was just going to add, I think in 2Ls, the hydrogen profile can be a bit distinctive. They have these profiles where the absorption is almost not there. You just get a broad emission feature in 2Ls. In 2Ps, I think it's very pronounced, the piecing. But in 2Ls, it looks like a triangle that's rising above the continuum.
Yeah.
That's not a rule though. That's true.
Right, right.
Yeah.
It's not a rule, but it's overabundant.
Yeah, let's say, I think I do, let's say subtle. Question mark. Yeah, I actually think it's debated from what I've seen in the literature. Any other questions about the type 2s? Okay, then let's move on to the stripped envelope supernovae. Was there anything else I wanted to say also? Oh, I just wanted to mention that, right, and actually figuring out what these are, what the progenitors are, you would ideally want to see the progenitor in pre-explosion imaging. That's very difficult because the system would have to be very nearby, and you have to have had very high resolution, usually Hubble Space Telescope imaging of that galaxy from before the supernova actually happened. And then you have to go back and check that whatever you think might have been the progenitor star actually disappeared. So it's a very difficult thing to do, but there have been a number of cases where there was a 2P supernova very nearby. People went back, looked at the Hubble Space Telescope imaging of the galaxy, of that location, and saw a red supergiant progenitor. So I'd say one of the things we do feel like we know is that in at least some cases, we have 2Ps that came from red supergiants. All right, so what are the types here? So I'm just going to write them down first.
Sorry, question.
Yes.
Being interested in the reverse engineering of that question.
Yes.
To an observer, there is no straightforward way of telling just from the emission spectrum or emission lines what was the progenitor of the supernovae once you're just observing the after effects?
Right, so you can get a hint because you can see what the composition of the ejecta was. And so, for example, once we're talking about type these ones, so these are stripped envelope supernovae, they're called that because the fact that they don't show hydrogen, and in some case don't even show helium, makes us think that the hydrogen and helium envelope was lost prior to the explosion. So that tells us something about the type of progenitor, but really exactly what, to be sure, you want to know, to know exactly what and what kind of evolutionary path it took before explosion, how it lost that envelope, all of that, you don't really know. Yeah. All right, one more. Right. So these are the stripped envelope supernovae. These classifications are based on spectroscopy. This is very, very difficult to do. We know that this is very difficult to do on the basis of light curves. Okay, so let's just step through this. The 1Bs, you still see helium, just no hydrogen. The 1Cs, you have no hydrogen and no helium, at least none observed. Then there are the 1C broadline supernovae, which I know a couple of you are studying. And here it's not about the composition. So it's the same composition as a 1C, but the BL stands for broad lines. And that has to do with the width of the absorption features. So this is a figure that is intended to illustrate this. So you see the 1C with some of the elements labeled. So this calcium 2, oxygen 1, silicon 2, iron 2. And if you imagine just smearing that spectrum out, which is what happens if the ejecta are basically have a very large velocity dispersion. Then the smoothed version of that spectrum, the blurred version, is the thing you see on the top. And so the oxygen 1 and the calcium 2 are basically being merged together to make one very, very broad feature. And so that's what we mean by 1C broadline supernova. And then just as with the two ends, so the two ends, there the 2 still means hydrogen, but now you're talking about hydrogen in emission instead of absorption. It's the same for the stripped envelope supernovae. You can have helium that's seen in emission rather than in absorption. And you can even have cases where you have no hydrogen or helium, but you still have narrow emission lines of carbon.
This is the case of emission?
This is absorption, the one being shown up here. So these are broad absorption lines.
But if I look at the calcium one, it seems like it's a peak rather than a value, or maybe it's really
no, I think it's a P Cygni absorption feature. So you see, yeah, it's absorption. Yeah, I guess it's hard to see where the continuum would have been on these, which is, I guess, makes it hard to say is this emission absorption. But these are features that are coming from absorption. Yes.
Why do those broad lines happen? Like, what is the connection between the velocity and the broad lines?
So why does a high velocity give you broad lines, or
yes.
why? Okay, right. So picture this is basically a hot gas, and so you have and it's some of it's traveling towards you, some of it's traveling away from you, and so the stuff traveling towards you is blue shifted, and the stuff traveling away from you is red shifted, and so the if everything were completely no velocity, then you would have no width. There would be just, you have no width. But once you start to increase the maximum velocity of the stuff coming towards you and the maximum velocity of the stuff going away from you, as you keep doing that, the line will get broader and broader, because the material that's absorbing the photons is now traveling with a greater distribution of velocities. So it's the width of the line. I think it's sometimes something that it's a sort of a subtle thing. So the actual width of the absorption feature is from the spread of velocities, but then the overall feature will also move. It'll usually be blue shifted because of the kind of net velocity of the ejecta as you observe it. So usually for a broadline supernova, people are measuring both the blue shift and the broadening. And they usually find that they track one another. So you kind of do both usually. Yeah.
Can you see indications of asymmetry in these broad lines?
Even if those things, for example,
we
didn't.
Yesterday, the kind of the shape of the line and how that corresponds to the kind of geometry of the emitting region, because 1Cs are.
Yeah, that's a good question. So I don't think people think that these must be very asymmetric explosions for a variety of reasons. But as far as I know, that's not usually on the basis of their actual spectral features. These spectral features it's very difficult to really, because with the broad lines, they're all blended together. And so it's actually quite difficult to do detailed spectroscopic measurements for a 1C broadline supernova. You can't, people are basically, they take a 1C spectrum and then they artificially increase the velocity to broaden the lines, and then they try to match it to what they see, essentially, is how you measure the velocities. But I think it'd be difficult to say much more than that on the basis of the spectra. Some of these objects do have, spectropolarimetry measurements, or they have radio observations, or other things that tell you that it's probably asymmetric. Oh, much later times, you can see from nebular features indication of asymmetry. Yeah, sorry, I didn't. So this kind of spectrum, probably not. But much later, you can start to see sort of splitting in the nebular spectrum, where you'll see a line here, then it has another line here, and then that kind of tells you that you're seeing something asymmetric. So yeah, it's definitely from the nebular spectra, but I think not from this. Yeah. Yes.
So is there like a association between broadlined supernovae and superluminous supernovae?
Oh, right. Yeah, I didn't. It's actually a good point. I should have listed. Well, yeah. So, okay, I should have listed superluminous supernovae. That's my fault. All right, let me add that here. Actually, completely forgot about that. Thank you. All right. I'm adding them to their sort of appropriate places. So these would be, okay, so now these are events where you would just classify them based on how luminous they are, which is why they're called superluminous supernovae. So there's essentially just a crude luminosity cut, where above that you'd say superluminous supernova, below that you would say regular type 1c. So superluminous type 1s, this is basically a type 1c. There are also type 2 superluminous supernovae, where again, that's just on the basis of the light curve. Okay, so and for this, so are there, you could ask, are there spectroscopic differences between a type 1c superluminous supernova and a regular type 1c? So yes, especially early on, there are certain features that you see in the superluminous supernova spectra that are different. But I think it's sort of hard to say, because you do expect the spectra to look different if, for example, your material is much hotter, which I think people suspect is the case when you're observing a superluminous supernova. And I know that there's been some work saying, oh, and also actually superluminous supernovae, these are technically, if you just got a spectrum, you might call it a 1CBL, because the features can be very broad and have very high velocities. But yeah, I'd say especially at early times, you know, these kinds of phases, the superluminous spectra and the regular 1C spectra do look different. I think at later times, they can actually start to look very similar though. And so it might be more to do with the physical state of the ejecta rather than intrinsically what exactly it is. Other questions? I think those are the all the main types of stripped envelope supernovae. Was there, let me just see. Okay, no. Right, so physically, what do we think explains why you see type 2s, why you see some type 1s? So as we've already discussed, we think that it has to do with how much of the envelope has been stripped before the explosion. And how you actually strip the envelope is a major open question in this field. I think today, most people would say that to strip the envelope for stripped envelope supernovae, you really need to do it through interaction with a binary star companion. And that's been I think that's been a change within the last decade in the field. People used to try to do it with single star evolution models, and then they realized that the winds are not strong enough. Yes.
Wouldn't, like, in any sort of stripping scenario, wouldn't there be like residual hydrogen left over for the supernova to interact with at some point?
Yes.
And create little flares with like.
Yeah, absolutely. Yeah, so the question is, if you've stripped the envelope, where did the envelope go? Exactly. Right, so in something like the object I showed you where you have this transition, that's part of why people get excited about these objects. So they say, oh, maybe this is the envelope that we've now found. But that has only been done for a small number of objects. And I think we're looking for signatures of that envelope has been lost. That's something people try to do. It's a little bit tricky because it would have happened quite a long time ago from our perspective. And so to wait until the ejector reaches there could actually take quite a long time. But if it were lost, I mean, in some cases you see quite a lot of material that must have been lost quite recently, like in the last century. But that's a different, that must have somehow then been synchronized with the explosion. Yes.
So then, like, have there been constraints on like finding the hydrogen envelope through like a radiooptical or something?
Yeah, so that's part of what Raphael was referring to. People try to look. There are radio surveys going on at the same time. There are optical surveys, and so for very, very old supernovae, we can look to see were they detected in the radio, and a fairly significant fraction of them are, but we're limited by how long we've been doing surveys on Earth. Yeah.
Like you'd only be able to see the envelope in signatures like that if it was lost through like wind or something, right? Not if it was stripped by a binary companion, then the envelope would have presumably been accreted, or are we assuming that some of it was lost during that process too?
Oh, actually, even in the binary stripping scenario, you expect the envelope to still be around. So it's yeah, I guess getting into the details of this is probably not where we want to go today, but when the binary strips the companion, well, exactly how all this happens is actually a major open question, but people think that you would actually expect the envelope to still be in the vicinity of the system. It's not going to, yeah.
It won't be completely accreted.
No, yeah.
So even with very high spins and high magnetic fields, with as you said, accretion and outflows, you would still expect some binary companion. Like those claims have been.
Yeah, so I think, and, I will say this is still actively discussed in the literature, but steady wind mass loss rates have come down. People have realized over time that they're not as strong as we used to think they were. So that's one thing. And so to actually, right, so that's one thing. And then in the meantime, it was realized that the vast majority of massive stars have binary companions, triple companions. They're part of these multi-star systems. And so for those two reasons and others, I think most people would say now that all of these objects that I'm writing here are the product of stripping by a binary companion. Yeah. Yes.
Is there any reason why type 2Bs cannot be like this kind of a stripped envelope? Because they are like type 2, but then they transform into type 2B. Oh, they are?
Yeah, that's fine. You could call it that as well.
Oh.
I think, yes, it's very partially stripped, yes. Yeah, this is all, I think in the literature, you'll see a lot of discussion about to what extent some of these things are truly a continuum and to what extent these are the results of very, very distinctive evolutionary processes. So for example, the 1BNs, 1C broadline supernovae, these are fairly rare types of objects with fairly strange properties. So 1C broadline supernovae, these are sometimes associated with gamma ray bursts. 1BNs have very, very homogeneous light curves. The optical light curves are almost exactly the same, which is unusual. And so I think, in particular, these two have been the subject of a lot of work trying to find some very distinctive channel that makes them, that would not make another type of supernova. Other questions? Would anyone like to add to anything that I said, or is there anything you disagree with based on your work? Okay, great. Okay, type 1s, right, we already talked about classification can be time dependent. Okay, so these are the primary classes of core collapse supernovae. And I'm now going to talk about some of the observational frontiers and what we've been learning from our recent surveys. Okay, so one of the big changes in the last really less than a decade has been that we have optical telescopes that are capable of basically seeing very large areas of the sky at a given time. That's because of advances in optical detectors. And so they can map basically the whole sky every night. These surveys have been trying to do supernova science in a much more systematic way. And I'm just going to generically refer to them as wide field surveys. And so LSST, would fall into this category. So one of the, actually, maybe I'll start with I'm going to switch the order of what I was going to do. So I mentioned this earlier, but what this lets you do is is a much more kind of systematic census than what we have been able to do in the past. And maybe I'll show you. Let's go here. I've just been emphasizing that in order to really classify a supernova, you really need to get a spectrum. But spectroscopy is expensive in the sense that you're breaking up the light into maybe 1,000 individual channels. And so you need significantly longer exposure times to reach the same sensitivity for a given object. And so a discussion that you've probably heard floating around if you've been in the survey crowd, LSST crowd, is how do we decide which of these transients we're going to get a spectrum of? LSST will generate 10 million alerts every night. So obviously you're not going to go and take a spectrum of every single one. And I think in the past, the problem has been that this has been done in a fairly ad hoc way. We look at the data from each night. You say, oh, this is a weird looking supernova, so you get a spectrum. And then, oh, there's another weird looking supernova, so you get a spectrum. But approaching things that way doesn't, maybe you'll discover interesting single objects, but you have no way to then go back and say, well, what was the rate? What was the prevalence of that weird object? How am I even defining weird? And so another very important thing to do is to do spectroscopy in a very systematic way. So in the last few years, one of these wide field surveys, ZTF, has been doing what's called the Bright Transient Survey. Another term for this is that it's a flux limited survey. And what that means is that rather than sort of pick and choose which supernova you spectroscopically classify, because you like this one, you don't like that one, you spectroscopically classify every single supernova as long as it's brighter than a particular threshold. And so that's what this flux limited means. So it's 93% complete. For this particular threshold. We can talk more about why this threshold was chosen if you're interested. So as of when I looked this up, which was about a week ago, there were almost 2,000 core collapse supernovae classified in this manner.
When do they spectroscopically follow up?
Right,
At
that's a very
the
good
time
question.
when it reaches its magnitude?
Right, so that's a good question. It depends. Yeah, I would say it's not, there isn't a, oh, we're going to do it at this phase of the light curve. Once it exceeds the threshold, now it's on a list to be classified, and then it's just classified at the first opportunity. So it's not necessarily classified when it's brighter than this. It might be a little bit later. I think there are a number of us in the room who have done dozens of observing nights on DVSP and Keck, where somebody gives us a list of 200 supernovae to classify, and we just go through and classify all of them, and we've learned how to game the right ascension so that we just keep as the as the sky moves, we're just classifying more supernovae. Yeah, so it can be late actually. For some of them, maybe you missed it when it was really bright, and now you're just catching it later on. So yeah, that actual phase is it ranges a lot. And yeah, so just to emphasize, the first large. There are many other types of transients, of course, type 1a supernovae. Those are the most common, actually, in a flux-limited survey, even though they're more intrinsically rare because they're more luminous. Tidal disruption events, all kinds of things. But since this is a talk about core collapse supernovae, I thought I would give that number. All right, so the most one of the most important things that comes out of a survey like this is rates. And so you can do something like, and I'm just going to, I can't give you all the details because we just don't really have time. So the paper you should look at with all the numbers is Perley et al. 2020, which gave some preliminary rates. And then there are a number of papers in the works to do this in much more detail for individual classes of supernovae. So by number, 72.5% of supernovae in a flux-limited survey are type 1a, which we haven't talked about. Those are the thermonuclear supernovae, 26.0% core collapse supernovae. And then you can break this up into subcategories. So
This is the volume or
this is just flux limited. Yes, so just by number. Yeah. Yep. And I'll give the volumetric rates in a moment. Core collapse supernovae. And then you can, yes, 72.2% to type 1. And then, right, you can also do it by volume. And here you have to do some, this is less direct. And so you have to make some assumptions. Essentially, the way this works is you say, okay, for a given luminosity, for a supernova given luminosity, I could have seen it out to this redshift. And then in this luminosity range, you maybe say that, because basically there are some core collapse supernovae that are very, very, very intrinsically faint. And so there are many of those that we just would completely miss because they're so subluminous. And so you have to say something like half of them fall into that category, make a correction. But anyway, this is now a little bit less direct, but by volume, the number is now 0.01, 5, or 6 per year. So this is literally, number of events per year within a cubic gigaparsec around the Earth. And then you can break this into each of the subtypes, and I'm not going to go through all of that. One thing I'll just mention, because it'll be relevant tomorrow when we talk about the relativistic explosions, and I know a couple of people work on the 1C broadline supernovae, you can start to say, even for a class of transients like this that is very rare and for which only very, very small heterogeneous samples existed in literature before, you can say that it's 3 to 5% of the core collapse supernova rate. And that becomes very important if you want to understand the progenitors of long duration gamma ray bursts, since these are the supernovae associated with them. It gives kind of a cap. Okay, so that's just a taste for the rates. And like I said, you can look at that paper for more detail, and then there are several more coming. Yes?
The thing that you just wiped out, but we didn't.
Oh, sure, sorry.
That it's 93% complete.
It means that even for supernovae that are brighter than that threshold, you only actually classify them 93% of the time. You miss some. And you might miss them because maybe when that supernova was discovered, the weather was terrible at all your observatories and you just weren't able to classify it. Or sometimes the survey is doing the whole sky and there can be parts of the sky that are not favorable. So maybe it's right at the horizon. And so the telescopes we have some physical limit where they can't go below a certain elevation. So situations like that, edge cases, but 93% is very good. Yeah.
What is the extra like 1.5% that don't fall into a bucket for the number?
All kinds of things, TDEs.
Okay.
Yeah, there's tons of other transients. Yeah. Yes.
Maybe you said this, but in terms of the dividing line between broad line and regular line, I mean, it seems to me likely it's a continuum, right?
Yeah.
And so you could actually make like a probability distribution based on the width, right? And so is it clear that there is two distinct populations, or is it just like, if I said a really broad line one, it would be 1% or something like that, I guess.
Right. Yeah. So we're trying to determine that. I would say that's not so clear yet.
It's not clear if they're really.
I think it's a little unclear.
So continuum.
Yeah, I think it's a little unclear still.
Where you put that cutoff. Okay.
Yes, I think that's true. I do think that people have still seen very different host galaxies for these types of objects. So that might suggest that it's not, maybe a continuum with a certain subset of the 1Cs or something like that. Yeah. Yeah, I think the type 1Cs from like I said, this is all still early days and we're still digging into this in more detail, but the 1Cs themselves do seem to break into several groups. And so some of them have really, really long duration light curves. They themselves seem to have several subtypes, which you probably can't actually really see on that plot. So you should look in the paper for more details. But one way that people, one very simple thing you can do to start to look for trends in these big samples of supernovae is plot their durations versus their luminosities. So it's duration on the x-axis and luminosity on the y-axis there. And where the sort of trends the transients have on this plot tell you something about what might be powering them. And what it is difficult to see, so you can look on my computer later or look in the paper, or look in this paper, is that, for example, the 1Cs actually have sort of distinct groups on a diagram like this. And then you can see on the left, you start to find things that are actually very, very fast. On the top, you see things that are very, very luminous. And so it's also a way to define kind of what does it mean for a transient to be unusual or for a transient to be exotic. And then maybe you'd focus some of your additional spectroscopic resources on those weird objects. So speaking of weird objects, in addition to being able to do rates, what I was just starting to get into is that you can see clear outliers. Today you can start to look for trends. So for example, in the type 2s, in this sample, there was a very tight correlation observed. And so in general, longer light curves were dimmer, but then it's the opposite for the two ends, where longer light curves tend to be brighter. For the hydrogen 4, there's sort of clustering. You can start to look at their kind of ensemble host galaxy properties. This is what Brian and I were just starting to talk about, where it's been known that there are certain supernovae types that seem to prefer certain types of galaxies, but it's very hard to really make firm conclusions if you don't understand how you've selected your sample. And so we're able to do this much more carefully now. And we've really only just scratched the surface here. But you know, things you could do, you could imagine doing, or maybe I'll generally just say, for those who haven't really thought about this, so core collapse supernovae, you'd expect some young stellar populations because they're from massive stars, which don't live very long. And so if when you're seeing core collapse supernovae happen, you probably have a young population of stars. So something we were discussing is that people think that discuss whether the binary stripping, the stripping of the envelope could be a single star process or a binary star process. And one way you could examine this is you could look at trends with host galaxy properties, because in the single star stripping mechanism, you'd expect the mass loss to be more effective at higher metallicities. But in the binary scenario, it would actually be the opposite. And so you can look at whether your rates of stripped envelope supernovae are more enhanced in galaxies of one or the other type. Something that's kind of interesting is that as part of these big systematic surveys, there have been a number of core collapse supernovae that are in very strange locations. So they could be in galaxies that have no hint of star formation whatsoever. So people discuss whether those are truly core collapse supernovae or they just spectroscopically resemble them for some reason, but come from some kind of different channel. Okay, so that's all I was planning to say about what we've started to learn from these very wide field surveys and these population studies. I've only really been able to give a hint, but are there any other questions about this before I switch gears a bit and talk about very early observations of supernovae? Yes.
I had a question about this plot.
Yeah.
You said that there is a characteristic grouping of 1C. Where are they?
Yeah, I think it might be, not sure how effective it's going to be to show on here actually.
Oh,
so
okay.
Just because of the, it's a little faded out, so it's hard to show the colors. So I think I'll refer people to this paper. I got the figure from this paper. You'll see it better there. Or you can come up afterwards and I can show you. Yeah. Yes.
So from these rates, are there any constraints on the rates for supernovae?
Yes, you can measure that very precisely. And it's actually in this paper, but I don't remember off the top of my head. Other questions? Okay, then let's talk about early observations. Okay, so why do you want to go early? Just to review what these light curves typically look like. You know, the optical light curve is something like this. And so by very early observations, I mean that you discover the supernova when it's still very, very young. So you're still very, very close to the time of first light. So the time when the photons first leaked out of the system. And today, what would we call early? I think early would probably be considered anything less than about 24 hours. It's gotten fairly routine to catch these in kind of the first few days, but the frontier now is really the first, I would say really the first 24 hours. Okay, so what limits this? There are a few things. One is that very early on, the emission is very faint. And so in order to actually catch this, it would have to be very nearby. So one problem is that you just are limited to the most nearby objects. Of course, if your telescope has more sensitivity, like LSST will, you might hope to catch this more often, even if it's a little bit further away. And then another challenge or another consideration is the cadence of your survey. So if you're only looking once a week, which is what surveys used to do, then you'll, come here, you might come here, then the next observation will be here, then here, then here. And the odds that you'll catch it right here are very low. And so you want a survey that has a very high cadence so that you really sample the light curve very well. And then you are more likely also to catch it early on. And then a third thing is the wavelength of your observations. So if there are certain things that happen very early on, I mentioned the shock breakout, there's sort of a post-breakout cooling phase that's at higher energies, X-rays, UV. And so if you're just looking with an optical survey, you're going to miss that unless you're very, very, very lucky. All right, so yeah, considerations. Not what I just said.
Knowing what T equals 0 is.
Yes, absolutely. Right. I'll add that here. I'll just mention, right, so you don't, when exactly can you fix the onset of the light curve, which is this time of first light. Sometimes people say time of explosion. We have to be a little careful because it takes some time for the photons to get out. So it's actually not quite the same thing. What else did I wanted to say here? Right, so early on, there are different powering mechanisms that can kick in. So if you're a little bit late in the optical, you're seeing basically the radioactive decay light curve. But I mentioned that very early on, if you can catch an event very young, you're starting to see things like the shock breakout. Interaction with the CSM, and this in particular can extend for a long time, but there are cases where it only is happening in the first, even the first 24 hours. So people really want to catch supernovae young because they want to find some of these mechanisms because they give you information about the progenitor system that you just don't have access to otherwise. So I'll say a little bit about some of each of these in more detail. Okay, so what is this, the shock breakout and then the post-shock cooling? So just to clarify the distinction, so the photons have to break out, and now they've heated the ejecta. So now you have just this hot gas. It is cooling back down, and as it does so, it's radiating black body emission, and that's what this kind of post-shock cooling phase refers to. So for a red supergiant, it's going to be less than around an hour. But you can actually have cases where you have not just the progenitor star, this is the star, but you could have some material around that star that is very dense. So this is material the star might have lost before it exploded. This would be the circumstellar material. It can be optically thick. And if that's the case, your shock breakout could actually be from the circumstellar material, not actually from the surface of the star. And that will make the signal longer, and it'll also make it at lower wavelength. And you can actually get a shock breakout, but in the optical band that you could see with an optical survey. And there have been cases where people have argued that that's what they saw.
The time you're indicating here is for the shock breakout.
Yes.
Shock cooling can be much longer.
Yes, right. Yes. So there's a shock breakout, and there's actually a beautiful plot. Did I include it? Oh, amazing. Okay, great. So this is a very nice plot. Burson et al. 2018. So they caught what they argued was the shock breakout and then that post-shock cooling phase. So the x-axis here is in log space. So the right behind Kishile's head, from my perspective, is where the 1 day is. That's just basically the peak of the shock cooling. Yes, the peak of the shock cooling is about 1 day. And then that whole radioactive heating thing, that's what we normally see in an optical supernova. But this was with, I think it was with Kepler.
Yeah.
Yeah, it was with Kepler. So that's why they had a very high cadence to see those earlier phases. Yes.
Also, as someone who doesn't really believe in less than an hour shock breakout, I
Yeah.
to point out that spike is not observed
Yep.
directly.
Yeah. Yeah,
So
totally fair. Yep.
It's kind of an open question.
Yeah, totally. Yes, absolutely. But I just wanted to show what Raim said, that the post-shock cooling phase is longer than the shock breakout phase. Yes.
I just wanted to add one funny story behind this discovery, which is the early shock breakout was actually observed by an amateur astronomer who was randomly staring at that galaxy, and the supernova happened to explode when the astronomer was just taking fancy images of that galaxy. So that's why in this case you have a serendipitous detection of a shock breakout, which has happened at least in one of the cases.
Yeah.
But this is again like this type of cadence is very rarely undertaken in sort of large scale surveys. It's very difficult to do this, but this was just one of those one-off things where someone just happened to be observing the galaxy.
Right. Yeah.
What event? What's this and what type of supernova?
What?
16 GKG.
Ah, thank you. Yeah.
I don't know why I asked that question. That wasn't going to help me. What kind of supernova was this?
Is it 2B, I
It's a
believe.
2B.
Yeah. Yes. Okay, so let's using this as our springboard. So it is hard to prove that that's what you saw. But there are some cases where it's at least argued that that's what was seen. I think probably the most famous one was in the X-rays, actually. So that was a type 1b, 2008D. There are also UV cases. This is a type 2p, this one, RP. And then there are optical cases. And I'll write down one of the ones I like, where they argued that this is a CSM, circumstellar medium breakout, rather than a surface breakout, which is why you would see it in the optical. What did I wanted to say about this? Oh, right. There are also cases in gamma ray bursts, where sometimes the gamma ray burst is argued to be a shock breakout. And we'll talk more about gamma ray bursts tomorrow. I think the most famous example of this is GRB. Okay. Ooh. So something I want to mention about all of these objects is exactly what Jared just said, which is that in all of these cases, the duration of the shock breakout is much longer than would have been predicted.
Especially in a class called low luminosity GLPs.
Yes. Yep. Yeah, so that's true famously for this object, also true for all of these objects. And what happens if you try to model this shock breakout, which is itself a very challenging thing to do, you infer radii for the progenitor that are larger than what you would have expected. So, gamma ray bursts, these are supposed to be from fully stripped carbon oxygen stars, but you infer a radius that's 2 orders of magnitude larger than what you would think such a progenitor would have had. And that's a puzzle. So why, Jared is probably the best person to wax lyrical about this, but some astericity effects. You can have also in the pre-explosion evolution, there are ways to puff up the progenitor, especially for the stripped envelope supernovae. Did you want to add anything to that?
Yeah, I mean, I mentioned earlier, you sort of have whatever time scale is the longest between, whatever time scale is the longest between the diffusion time, the light crossing time of the envelope, and the some geometric time scale. So I like the fact that red supergiants have these huge convective cells. So actually the shock will break out of the valley before it breaks out of the mountain peak. And that kind of shock crossing time can set this time scale. But if you have it in a diffuse, fluffy outer circumstellar material, that can also be part of it. If you have an oblate shock breakout, then you can also have things wrap around, and that time scale can also smear this signal out.
Yeah, great, thanks.
Do all of these show no signature of CSM interaction?
As far as, okay, so I guess there's a caveat to that, which is that there's limited multi-wavelength data for these objects. So for example, this object had just an optical light curve and basically one filter. And I think they had one observation at late times of a color, which showed that it was blue, which does support that it was some interaction kind of thing, but had no spectroscopy. So, and there's no radio observations. This one had very extensive multi-wavelength observations, but nothing that you would call a kind of classical CSM interaction. So no narrow emission lines in the optical spectra, for example. But the setup for these sorts of things is that, you know, even if you had a star and a CSM, that by the time you're actually seeing the emission, the photons have just broken out of this outer region. And so there's actually nothing you wouldn't necessarily, as long as it's very confined, you wouldn't actually expect to see narrow emission lines. You're sort of too late by the time you've actually discovered it.
The breakout is how we'll see over V.
Right.
You still have a lot of like,
well, not necessarily.
Okay, no, it could be very, very like.
Yeah, I mean, if this is very compact,
yeah,
and so there's, you know, your profile, it's something, it's almost like you've just dropped off this cliff, then I guess you wouldn't necessarily expect that. So if the breakout is.
But then the radius wouldn't be much larger than the stellar radius.
I mean, in some of these cases, it's inferred to be.
No, that's what I'm saying. If you had very compact CSM,
yeah,
you also wouldn't have a much larger radius. Like the breakout wouldn't be at a radius that's much larger than the stellar radius.
Okay, yeah. So I think there are. So one thing is, how long does it take you from seeing this thing to actually then getting a spectrum? Yeah. And I think what I'm saying is that even if this is actually significantly larger than the progenitor, by the time you get a spectrum, in all of these cases, you'd be out. Yeah.
Yeah. What if you didn't have an optically thick CSM around?
Then the breakout would be from the surface of the star.
And then you could register it, right? And you get the spectrum.
So then it depends on what the, yeah, so, okay, there are many different configurations you can have for the circumstellar material. One configuration, just cartoon, that's popular to try to deal with some of this, is that you have a very dense and very confined CSM. Why you would have this? You probably need some kind of, you know, maybe there was some merger and then you had a supernova, right, synchronized with that, something like that. And then what happens outside that, you could have more CSM, but then to see signatures of interaction, like an interaction emission line or luminous radio emission, then that just depends on the density that's out there. And that's true whether or not you have this very dense CSM or not. Okay, I think that's all I wanted to say. Yes.
So I just had a question about like the physical interpretation of these two peaks. So
yeah,
you know, you have these two bumps. So the first bump that's like the CSM, and it's like shock is deposit its energy, and that's kind of like what Brian maybe talked about yesterday with the pure explosion case, where it's just this hot material that's expanding and then it rises and then.
Yeah, that's the second, the hot material expanding black body. That's the post-shock cooling.
Yes, and then
phase.
Then the second bump is just the radio. Like
that's the radio. Yeah.
The rest of the ejecta.
Exactly. Yep. They're hot. Yeah. There's radioactive isotopes in the ejecta. And then their radioactive decay products are sort of reprocessed through the ejecta, and you get, again, black body radiation, but through a different series of events. Yeah. Okay. All right. So that's shock breakout. Right. We have not seen very many cases of this, is basically the summary. And even the cases that we have seen, you could reasonably dispute what exactly was seen. Like for example, some people argue that this was a jet. Okay. Shock cooling radiation. Right. So this is the second peak. What did I want to say about this? Okay, so this is longer time scales, as we've already said. Here, there are many more cases where this has been argued to be seen, and I would say it's not particularly controversial. So in the optical, you'll see maybe an early excess. This is our main peak. So basically the second and third of those you see fairly regularly. It's very common in particular in type 2b supernovae. And the picture here is that you have some low mass So it's most common to see this in type 2b supernovae. It's very routine. And so that's led to some inferences about what the structure of these events look like. So in this case, it's not a star CSM, it's more like star and then extended material that's still part of the star. The difference is only whether it's still gravitationally bound to the star or not. But the shock cooling emission of this extended stuff is what produces that first peak. Yeah, and I won't say too much more about this, but just this is fairly routine to see, as long as you get observations within the first couple of days. Okay, CSM interaction. So I think the thing that gets kind of confusing about this is that many people have strong associations with what CSM interaction is. And many observational supernova people picture type 2N supernovae, where in a 2N, the luminosity of the light curve, the main light curve, is really being produced by this mechanism. However, what's being sort of increasingly recognized is that it can also contribute at early times in a wide range of events. So there are discussions about the early light curves of type 2s. There are discussions about the early spectra, again, of type 2s. So in the case of the spectroscopy, what's happened is that people have started to get spectra at very early times, so just the first day or two from the discovery, and seen things that look kind of like 2Ns, these emission lines that are just there for the first couple of days and then they disappear. And so the idea there is that the material had to have been fairly confined, because very quickly the shock ran through it and was out. I think maybe I included a sequence of one of these objects. Okay, yeah, this is a famous object where this was seen. So early on, so you can see the first few spectra are all within, all within a day. And then they're highlighting certain high ionization species that appear and then quickly are gone by the time you're at a day plus. And so people realize that if you do what's normally done, which is you wait maybe for the peak to classify events, you'll miss a lot of information about the material that's most closely confined to the progenitor, which corresponds to the mass loss that happened really, really shortly before the explosion. All right, I think, yeah, we only have a few minutes left, so I'm gonna just talk about some of the things to be kind of aware of for the future. I wanted to highlight some of the work that Nabil has done because with ZTF, we've gotten so good at identifying young supernovae that this is now being done fully autonomously. And so Nabil recently had an astronaut announcing a type 2 supernova at 40 megaparsecs that was fully autonomously discovered. And then the Swift Observatory has this program now where you can autonomously slew it. So you don't even need to get approval. And so they got Swift observations just 6 minutes after the initial optical discovery, which is a very different ballgame from what we've been doing before. All right, so the future. Nabil is the future. I'll just put your name. Okay, autonomous discovery, definitely. And very essential because future surveys, okay, so not LSST, but other surveys are going in the direction of higher and higher cadence. And so Ultrasat, for example, would be a UV survey, which in addition to actually being in the UV, which we haven't really had before, the cadence is 5 minutes. And so you're not going, you must autonomously discover and trigger. You can't manually trigger observatories. Right, so of course LSST, that's what we're here for. I think many people are excited about what it will teach us about the pre-explosion activities of stars and also about their power sources, because we have struggled to follow light curves for a long time when they become faint. And that's what you need to do to figure out, was this nickel, was this accretion, was this magnetar? On the X-rays, you want to do shock breakout. We again have the first X-ray wide field surveys. So this is launch 2024. This will be, I think, 2027 is the current plan. There are small surveys focused on nearby galaxies, and I think there will always be room for that. You can look up DLT 40 for an example of that kind of thing, because there's a lot of value in finding the most nearby supernovae as early as possible. Okay, maybe we are right at the 5 seconds till 12:30, so I'm going to stop there. And if you have any final questions, I don't want to keep you from lunch. You're welcome to come chat with me. I'll be there. So thanks.
Right, questions for Anna?
Oh, sure.
Maybe this is kind of a meta question, but going ahead where we have, huge numbers of light curves and possibly postage stamp host galaxies for huge numbers, do you think our classification system will change, that it will be decided that we will say, okay, something with this wiggle that happens in a star forming galaxy is this, and do you think we will sort of stick with these historical things? I mean, I would say the record in astronomy is we will stick with the historical things.
Yeah.
But is that the most useful thing, I guess?
Yeah, that's a good question. I'd love to talk more about this over lunch. I agree with you that the historical record would suggest that we will continue. I mean, we have in the stellar world classes of objects named for a prototype that we now know is not even a member of that class. So I guess what could really, for so many of these objects, we know so little about what the progenitor was. And so something you could imagine is if we really convinced ourselves of the type of mechanism that made this object, then maybe you start incorporating that into the naming scheme. Like when we say gamma ray burst versus collapsar, we're kind of distinguishing between what something looks like and what we think it actually inherently is. So maybe one day we would get to the point where we're incorporating what something actually is into how we refer to it.
I guess, yeah, I think that can be dangerous, but I guess my point is just if you have if you have abundant data that you didn't have before, like the host galaxy of each of them, or you have a much, maybe it's just not one characteristic that you want to classify, but you want to say, okay, that's technically a narrow line, but it happens in a region where we only see broad lines, or some, or something where it's, or anyways, this is just maybe it's not useful in the end, but unless you can, as you say, peg it to some physical system. Okay.
Yeah, maybe we'll realize some of the distinctions we used to make are no longer useful. So maybe some things will merge. I'm not sure.
Right.
Yeah, we can chat more over lunch.
I'm curious about, you said something about one of those serendipitous events with the shock breakouts. You said that one of those gamma ray burst registrations potentially could have been a jet, and some people think that it was a jet. Why yes and why not? Maybe.
I was referring to a very specific. So you can look at if you want a lot more details on this. The paper is. It's just very difficult. The problem is that with the really, really well-studied events, the problem is always that it's very difficult to explain every part of the electromagnetic spectrum. So you have some model that works for the UV, optical, X-ray, and then you fail to make the radio. Or you have a model that explains two of them and then not the rest. And so this paper just went through, I thought it was a nice paper. They went through several different possibilities for what they thought it could be, some kind of relativistic shock breakout sort of thing, more like a wide jet, and they just describe the pros and cons of each of those. And I don't know that we have time to do all that, but this is the reference if you want to look.
From your light curve perspective, observational perspective, what would have to be kind of checked to say, it's a jet?
That's more then you have to be talking about the radio emission, the X-ray emission. You can't just be looking at the optical light curve. Yeah.